Hi, welcome to the third day of XDC. Let's start with the opening session. As usual, we will go through all the sponsors of this conference. First of all, thanks Igalia for being Platinum sponsor and organizing this amazing conference. Then the list of gold sponsors that we have. Thanks Google for sponsoring. Thanks Collabora, ARM, and Microsoft. Also, I would like to thank our silver sponsors, FEXEMU, the Linux Foundation, AMD, and Qualcomm. And finally, I would like to thank bronze sponsors, the Kronos Group, and Codeweavers. Thank you so much. Also, I would like to thank our supporters, Turing's Office of A Coruña, and the local Linux user group called gpool. Similarly, I would like to thank Igalia for the welcoming event on Monday. The coffee breaks sponsored by the XOR Foundation. Thank you so much. Coffee breaks are really needed. Thank you so much, Igalia, for the lunches. And now I would like to go through some important information. Before continuing, I would like to tell you that we found some items lost during these days. Yesterday, there was a laptop charger here inside of this room. Just in case, if you know if it's yours or you know the person, just let me know and we will give it to you. And also, there was a green cup on Tuesday, I think, outside, that we can also give it to you. And similarly, another thing, before I forgot, you can submit lightning talks even today until the coffee break in the afternoon. Yeah, okay. So yeah, if you have any topic that you would like to present in that 5-minute format without QA, please, I encourage you to submit a proposal today. We have the Wi-Fi as usual. As you know, we have a code of conduct in our community. By being registered in this conference, by being here, you abide to it. And if you need to report any breach, you have here the list of committee members, and also there is a phone number to call to the committee. For the program of today, there is no changes. As far as I know, at least. So we will start with a talk by Boris. We continue with DRM, MSM, etnaviv, debugging GPU faults. By the way, this talk is going to be given by Danilo from the hotel because he's a bit ill. We have then Wayland cells for embedded systems, the lunch break, Wayland driver for wine and windowing, the usual state of XOR foundation, and then we start with the lightning talks. Again, remember that you can submit them along the day, but the deadline is the coffee break in the afternoon. For any kind of announcement, asking remote questions to the speakers, use our matrix room. The link is there and also in the website. You can also follow us in Mastodon, where we will be posting as well photographs of the speakers, and you can engage with our community manager. And that's it. Thank you so much, and enjoy this day. Thank you.
Hello, everyone. So I'm Boris Brezillon, working for Collabora.
Hello, guys. So I'm Danilo, and I'm working as a kernel engineer at Red Hat, mostly working on the Nouveau project and general DRM infrastructure.
Yeah, so for those who were expecting superhero stuff, I'm sorry, that won't be about that. So yeah, I've been working on the Pen4 driver, the driver for new ARM Mali GPUs, and also a bit helping with the PowerVR driver. So what this talk is about is the work that has been done recently in DRM to help support the new use cases for the new drivers and for the new hardware. So one thing I noticed when I switched from the old generation Mali GPU to the new one is that clearly the kernel driver is being pushed away. Like new graphics API, they want more control, which means the user mode driver also gets less control, but it still has to pass these information to the kernel driver. So it kind of overlaps with what the kernel driver was doing before. And on the other side of the picture, we have hardware that do more and more. Nowadays, I guess pretty much every GPU has microcontrollers executing firmware that, at least for the recent version, that those firmware actually take care of scheduling themselves, which was originally done in kernel space. So there are actually good reasons to do that. Like if the microcontroller just has to deal with GPU event, that means it lowers the latency, and it can also take better decisions in terms of power efficiency, like shutting down blocks when they are in use, and that can be done much quicker than if the kernel was responsible for that. So that's one thing. On the other side of the picture, the user mode driver gets more control, but that doesn't mean we should allow it to do anything. We need to make sure the system is still usable when user space is doing silly things. So despite having less responsibilities, we still have to implement a lot of stuff to make sure the system keeps running fine when the user mode driver or the application does something wrong. Because the original DRM framework were not designed for some of the use cases we want to support, that means we don't have any helper functions to do all of that. And what was supposed to be less work to do ended up actually being more work to do, because we have to add these new infrastructures. And of course, there are new features to support for new graphics API. So yeah, it's not that simple. So I'm gonna focus on the kernel mode driver to firmware interface. And I'm going to let Danilo focus on the other side, like KMD, UMD interface. One of the big challenges we had with new hardware is this firmware-based scheduling. Like the fact that the firmware is now in charge of picking up an entity, scheduling entity, and the queuing job from here, and then queuing that to hardware queues. Before we had such firmware scheduling, it was basically the kernel that was doing that. Like the kernel had a single scheduler, and it was being attached several scheduling entities, and then the queuing job from there based on some priority and some scheduling policy, like picking round robin or FIFO scheduling policy. So how do we move from a solution that's based on the assumption that the kernel is in charge of the scheduling to something that assumes that the scheduling is completely delegated to the firmware? Well, if we look at the DRM sched design, it's actually twofold. The first thing DRM sched takes care of is making sure that the job waits until all its dependencies are met before being pushed to the hardware. And that, we want to keep it, because we don't want to re-implement the same logic in all drivers. So we somehow want to use part of the DRAM scheduler. But what we don't want to keep is the actual scaling part of it, like being able to pick from different entities and control the hardware queues directly. So we need a solution to make this fit in the DRAM scan model. And what Intel people came up with, I don't know if that's Matthew Prost's idea or if that's other people's ideas, but what they came up with, and that was Matthew posting the patches, was to make the DRAM scheduler, the kernel side scheduler, as dumb as possible. And by dumb, I mean that all it does is passing jobs from the scheduling entity to the firmware directly, basically. I mean, you still have a backend to translate jobs into something the hardware can understand. But other than that, there is basically no scheduling in there. It's just passing the jobs around. That's actually implemented with the new policy, which is called single entity scheduling. And with this solution, we can keep DRAM sched entity dealing with all the dependencies, and we can also make sure that the actual scheduling is passed to the firmware. So with this solution, it works, I mean, but we still have a problem in that the DRAM scheduler, originally, it was designed to be dealing with one hardware queue directly. And that means that they plan for one thread, and this thread will pick jobs from different entities. If we go one entity per scheduler, that means that we now have one thread per scheduler, and I mean, an entity is basically just a GPU context, so you can have hundreds of them in the system. I mean, of course, you won't necessarily have that many, but that's still something that can happen. And if we go for one thread per entity, that means that the number of threads explodes. So one solution Matthew came with is to replace this thread we add by a work queue. And this work queue, we can actually reuse them across the scheduler, the GPU, the DRAM GPU scheduler, which means you can have one work queue for all your entities, and this way we don't have that threads explosion I was talking about. And of course, the single entity scheduling pass is basically a lot of if checks that just bypass the whole scheduling logic, because we don't want any of that. We want it to be as fast as possible. So it actually looks like that. I won't go into details, but basically what we did is replace this big function we had in the thread and split it in several parts. And each part is being a work that's queued to the work queue that was passed at initialization time. So, I mean, that works pretty well, and it solved the problem that we had. And I think people are mostly okay with it. It should be merged pretty soon, I expect. But then, for Mali GPUs, we had actually another problem, which is that the number of scheduling slots you have on the firmware side is quite limited. I mean, it's as low as 8 slots, and you can't just limit the number of contexts to just 8. That doesn't work. So what we had to do is add another layer of scheduling, which is just private to the driver. And what this layer of scheduling does is it's not scheduling jobs directly or entities. It's just rotating the entities that are waiting for some GPU time. And yeah, it's basically assigning new slots to waiting entities after after some entities spend some time on the GPU. So yeah, that's what we ended up with. I know that Sima suggested another approach, which is representing the slots with some kind of resource that we can ask for, and then using the DMA fence to control or to serialize access to firmware slots. I did play with this approach. The problem with that is that as soon as we consider adding user mod queue at some point, it's kind of tricky to get it working because it's based on the assumption that you can know what the job, when the context submit jobs to the queue, and as soon as you have user mod queues, you're not in control of the queue itself. It's user space controlling it. So in the end, we ended up with just this indirection in the scheduling logic in Mali GPUs, but we're still really reusing all the rest of the DRAM sched stuff. So yeah, that was it for the firmware scheduling part. Now I'll hand it off to Danilo, which will talk about other stuff.
Right, so in the second half of this talk, I want to focus a little bit more on the interface between the user mode driver and the kernel mode driver, and want to start with a brief introduction of how the Vulkan API influenced such UAPIs, resulting into VM-bind style UAPIs and how those work. And then I want to take the majority of the time to introduce a new DRM common component called GPU VM, which is basically aiming at helping drivers to support and implement virtual address spaces, which ultimately is also useful for implementing VM-bind style UAPIs. So looking at Vulkan once, so Vulkan has some new requirements which are not really working out very well with existing UAPIs, such as explicit synchronization. So looking at traditional UAPIs, they used to do implicit synchronization, which basically just means that the buffer object, so the actual portion of physical memory, is serving as synchronization point, whereas with explicit synchronization, jobs carry dedicated lists of sync objects serving as, so one list serving as list of dependencies that must have been signaled before the job is allowed to be executed, and the second list being signaled once the job is completed. So other requirements Vulkan comes up with is some kind of advanced virtual memory management, which ultimately led to new VM-bind style UAPIs giving user space the control of the GPU's virtual address space. So speaking of VM-bind style UAPIs, I want to quickly go through 3 ioctls, which I think represent the key of this API, or of this kind of API, which is vminit, which just creates a new GPU virtual address space. So drivers would typically create a new context there, set up page tables, and all this kind of stuff. So then we have the actual VM-bind ioctl, which actually binds memory to a virtual address. And it typically carries the operation type, so whether it's a map or an unmap request, obviously the virtual address for the mapping, the size, the buffer object or the handle to the buffer object backing this mapping, and the offset within this buffer object. And of course, the synchronization objects I mentioned on the previous slide, like the waitlist and signal list. I also want to mention that it's typically legal for map and unmap operations passed through VM-bind to arbitrarily span across existing mappings. So drivers need to be able to deal with that. And I'm mentioning that because GPU VM, which I will talk about later on, provides some helper functions to deal with that. And there are typically also synchronous and asynchronous variants where the latter is used for implementing bind queues. Then we have the exec ioctl to execute a command buffer, and I'm mentioning this here because it works a little bit different as with traditional UAPIs, where the exec ioctl would basically carry the buffer objects containing the command buffers. So with VM-bind style UAPIs, the exec ioctl just carries a list of virtual base addresses where those command buffers are mapped, and which were previously mapped with a VM-bind, obviously. The size of the command buffer and also sync objects, so again, the waitlist and signal list. It's also worth noting that command buffers or shaders can operate on the whole virtual address space, which ultimately leads to the requirement of validating all underlying buffer objects backing this virtual address space for an hexagonoctal. So in this sequence diagram, I tried to come up with a sequence of VM bind and hexagonoctals, so all asynchronous, and try to depict how fences are passed around between user mode, kernel mode driver, the DRM schedule, and the hardware. However, I don't want to go into detail on that one because that takes too much time. So if you're interested, you can check out the slides later on and have a look at that. So now getting to DRM GPU VM, as already mentioned, it's a new common component to manage a GPU's virtual address space and was motivated by, but is ideally not limited to, VM bind style UAPIs. So it just means GPU virtual memory, and originally it was called the DRM GPU VA Manager, and it is still called DRM GPU VA Manager in the kernel release v6.6 that's going to be releasing soon. The reason for renaming that, and it's already renamed in DRM Misc Next, was simply that it turned out that drivers typically call the structure they are embedding the VA Manager in just simply a VM. And also the kernel documentation for asynchronous VM bind and VM bind locking, Thomas Hellström recently pushed, calls it GPU VM, so I just wanted to go along with that naming scheme. And it also turns out that it makes the API naming a little bit more consistent. I also want to give a shout out to Dave Early at this point, who suggested having such a component in the first place. Now, what does DRM GPU VM do? So it basically provides the infrastructure to track virtual address allocations and mappings and connects those mappings to their backing buffer objects, which are DRM gem objects. And as already mentioned, when introducing VM bind, it also provides a mechanism to break down complex map and unmap requests into a set of operations which can be directly performed by drivers. So for instance, when mapping requests intersect with existing mappings, or you have partial unmap requests, so this kind of stuff. So all that comes with v6.6 of the kernel that's already merged upstream. There is also a patch series that's upcoming, so this will be merged soon into DRM Misc Next, so I think we have consensus on that. And yeah, I think I've written in the slides that it targets v6.7. I think that isn't true. It's more like v6.8 because actually DRM Misc Next might already target v6.8, I'm not sure. Either way, it basically consists of generalizations for implementation to improve performance in this context. The first one being to implement common DMA reservation for gem objects that are local to the GPU VM and the tracking of external gem objects. So local just means that this buffer object is only mapped in a single virtual address space, whereas external means the buffer object is potentially mapped in multiple virtual address spaces. So the reason we need that is because, as I already mentioned, with an hexagonoctal, for example, you would need to validate all the buffer objects that are backing the virtual address space, which comes down to you need to lock them, and hence you need to know them in order to be able to lock them. And the only real way to know them would be to iterate through the whole virtual address space and iterating through all the mappings within the virtual address space, finding their backing buffers. And that's potentially a heavy operation because apparently there are applications creating multiple hundreds of thousands of mappings, if not even millions. And yeah, that would be a heavy operation. So the idea is to have a common DMA reservation and therefore also a common DMA reserve lock for all objects that are local, so only mapped once or only mapped in the single VM, such that we cover them with a single mutex lock basically. And then we only need to iterate through the list of external objects that we separately cached. And yeah, that makes the whole thing way cheaper, especially when we run into contention where we actually would need to multiple times iterate through a whole virtual address space otherwise. So it also comes with some helper functions to lock all the backing buffer objects. This implementation is mostly based on DRM exec, which was implemented by Christian König from AMD. So DRM exec is basically a helper that takes a set of buffer objects, locking them and dealing with contention and all this kind of stuff. So the last feature I want to mention is caching evicted gem objects. So the reason for that is basically the same as for having a common DMA reservation and tracking external objects. So once we got the whole virtual address space locked, all the backing objects locked, we would want to validate them potentially. And while we could just run through the external object list for that, we don't know the local objects. So we only know the common DMA reservation. Again, we would be left with running through the whole virtual address space mappings and find the backing objects. So instead, we just cache them once they are evicted, and then we have a dedicated list that we can just validate. Now, I want to talk a little bit about the structures of DRM GPU VM. So first of all, and that's pretty obvious, there is a structure called DRM GPU VM, which just represents the virtual address space. And this structure has a red-black tree, which keeps track of all the mappings within this virtual address space, which are represented by a DRM GPU VA struct. So originally, we wanted to use a maple tree for the same reason MM came up with the maple tree, using it for VMAs. But it turned out that there are some use cases where the maple tree simply just works well because it requires allocations for internal nodes to keep track of objects. And we are potentially using it in the context of updating the virtual address space from DMA fence signaling critical sections where allocations are actually a problem. Now, the maple tree provides some options to pre-allocate nodes, but those come with some limitations, and actually we are unfortunately running in those limitations. So the only thing we would be left with is using atomic pages for allocating nodes for the maple tree to track objects when we update it. But this also isn't really desirable. So for now, we are just stuck with a red-black tree, unfortunately. So another structure I want to mention is the DRM GPU VM bow structure, which is basically a representation or an abstraction representing a combination of a VM and the gem object. And the reason we have that is just to provide an indirection to have a little bit better structure of connecting mappings to their backing buffer objects and making certain accesses a bit faster, such as finding all the mappings of a given buffer object for certain VMs. Another reason we have this abstraction is because it comes in handy when trying to track the backing buffer objects in the Ext object list and the evicted list I just mentioned previously. Because we potentially have buffer objects mapped in multiple VMs. And if we want to track those buffer objects in multiple VMs, we would basically need to insert them into multiple lists, which requires multiple lists in the list, so multiple list heads within the buffer object. So it all comes down to that this is a limitation from the implementation of lists within the kernel. So using the DRM GPU VM bow representation comes in handy because it already is per VM and per buffer object, so it's the perfect structure to track within those lists. There is also the DRM GPU VM exec structure, which is basically just a wrapper around DRM exec, connecting it to DRM GPU VM, providing the abstractions to unlock the virtual address space mappings backing buffer objects. And then the last structure I want to mention is the DRM GPU VA op structure, which serves basically as the base structure for map, remap, and unmap operations. So those are the operations that DRM GPU VM can create for you if you pass in mapping requests that are not directly applicable to the virtual address space. So because that's a little bit abstract, I have an example here. So let's assume we have a virtual address space with 3 mappings. The first being the buffer object A that's mapped from 0 to 3, another buffer object B mapped from 3 to 4, and a third one C mapped from 4 to 7 within the virtual address space, but also having an internal offset, so an offset within the buffer object of 2. And now we could get a VM bind request to actually map another mapping of C with the offset of 4 from 1 to 5. So you see that in the request line. And in this case, we cannot directly map this because there are mappings in the way, so we first need to create some space. And rather than doing all the calculations needed for that within the driver itself, you can just pass it to GPU VM and tell GPU VM that you would like to create this mapping, and then GPU VM returns you, or actually it provides 2 ways to return you the sub-operations to execute to just make that happen. So one way is it provides you with callbacks. Another option is to provide you with a list of operations, which is useful if you have several stages of your VM-bind implementation. So like the ioctl phase where you need to iterate through the operations, maybe in the run job phase of the DRM scheduler, and in the free job phase to free page tables, for example. So in this example, if you pass it to GPU VM would return you 4 operations. The first one being a remap of A to create some space for the new mapping, so remapping the buffer object A that's mapped from 0 to 3 to 0 to 1. It would give you an operation to unmap B entirely because it's just in the way. And it would give you a remap operation to remap C that's mapped from 4 to 7 to 5 to 7, again to create some space. And it also adjusts the offset of the internal buffer object because since we're cutting it off at the beginning, we also need to adjust this offset to make sure that it still has the same contents. And then it finally would repeat the original mapping request to you now that we got space. So this is just for convenience that you can use it in a common code path. So that's a diagram basically depicting how Nouveau implements VM-bind using DRM GPU VM throughout the 3 stages, the ioctl phase, run job, and free job phase. I'm not going to go through that in detail because I don't think we have time for that. But I still thought it might be interesting, hence I put it in the slides to, so in case you want to check that out later on. And finally, I want to give a quick driver status update on Nouveau relating to the UAPI changes and DRM GPU VM, since Nouveau was basically my pilot for implementing the GPU VM component. So the new UAPI implementing VM-bind was merged upstream. It's going to be released in v6.6, and it should be sufficient for NVK to implement a fully functional Vulkan user mode driver. So I think I don't need to say much more about that. This was already covered by Faith and Carol. So there are some upcoming changes. So first of all, Nouveau is going to also pick up the DRM SCAD single entity model that Boris was talking about. So the patches already exist. We are only waiting for the DRM SCAD patches from Matthew to land. And it will also pick up the performance improvements due to the tricks implemented in GPU VM I mentioned previously. So those patches are implemented as well. So we're just waiting again for GPU VM to just land. Unfortunately, there are also some missing parts. So for example, user pointer support, which actually might be postponed a bit more in favor of landing the GSP patches instead. And we're currently not utilizing the DMA engine for page table updates. So everything Nouveau does currently is executed directly by the CPU.
Yeah, I'm gonna give a quick status update on Pentor too. In terms of UAPI, Pentor is pretty much the same, following the same model that Nouveau and XE, the Intel driver, are following. We have a VM-bind ioctl, we have submit ioctl, we have ways to create context. And of course, Pentor is using all of the new stuff that we discussed before, like DRM SCAD single entity and then VM-bind, DRM GPU VM to implement VM-bind. What's missing? More testing. We're still discovering bugs because we are just starting testing it with GL workloads. And the other big thing that's missing, I guess, is having a Vulkan driver that's functional so we can actually exercise the VM-bind stuff, all the features of the VM-bind stuff. Another big thing that's missing is transparent buffer ejection, because right now we just pin the buffer the memory to the buffer objects when they are mapped to the GPU, and they stay pinned for the whole lifetime of the mapping itself, which means if the system runs out of memory, we're just screwed, and the OMM killer is likely to kill the apps. Yeah, as Danilo said, we're waiting for patches to land, and after that, I guess we are ready to merge the driver itself. Yeah. Quick word about PowerVR. Same again, based on the same things, DRAM-SCHED single entity, DRAM GPU VM. Apparently, they do pass the 1.0 Vulkan CTS already, which is good news. And it's making use of all the new fancy stuff, except for one thing, which is the VM by ioctl. So right now, they do implement synchronous asynchronous mapping with two ioctls, which are called VMMap and map, which basically does what a VM bind synchronous ioctl would do, except it's not named the same way. But they do plan to add support for asynchronous VM bind pretty soon. So I guess we are in good hands there. Again, transparent buffer eviction, it's not implemented, and it's likely coming as a second step once the driver is merged. So that's pretty much it. I don't know if you guys have any questions. There's one over there.
Yeah, thank you. Question to Danilo regarding GPU VM. So as far as I understood, or maybe I'm misunderstanding, this supports a single address space for the whole process. Is it correctly or not? So,
sorry, I didn't hear you.
Yeah, sorry. So basically, for example, our GPU support per process page table, so each process has its own address space. Is it possible, or how feasible, how hard would it be to adopt GPU VM in such a case?
So you're free to create any address space you want. I mean, there is an ioctl to create a VM space. If you want to have several per process, it's up to you. I mean,
so it is already there, and we can just start poking.
Yeah.
Thank you.
It's just up to the user mod driver to do what it wants. Usually, you have one VM per VK device.
Oh, so that was better. Thanks. Sorry, I wasn't getting it.
So if I understand correctly, like if you want to remap from one backing buffer to another backing buffer in GPU VM, like you decompose that into a set of unmaps and maps like to unmap previous buffers. Have you figured out how to deal with like if you do sparse binds while the application is possibly accessing it, the application then expecting like maybe a default value like zeros instead of a VM fault?
So your question is basically about how we implement sparse bindings with that?
Sparse bindings, well, the application might be accessing it, yeah.
Right. So in one of the first patch sets, I had a concept called regions, where you would basically create a region first, and then this region represents a sparse mapping, and then applications can go ahead and request normal mapping, so we would store them as GPU VA structures then within a region, but that was dropped because we can simply just have a flag for DRAM GPU VA structures indicating that it's a sparse mapping. And once you get actual memory mappings from user space requested that are actually having a backing buffer, you just split them up as you would split up normal mappings when they intersect with previous already existing mappings. So it would be exactly the same case, just without a buffer object and with a sparse flag.
No more questions? Thank you.
this one's always on. Yeah, it's okay. Yeah, please. Yeah. Oh yeah, sure. Yeah. Oh, that's fine. Okay. Hello. Hi. Good morning, everyone. And thank you for joining this talk on the DRM MSM display and graphics update. I am Abhinav Kumar from the Qualcomm display team, and along with Dmitry and Rob, we co-maintain the display upstream driver for the Qualcomm chipsets. And thank you to XDC for giving us an opportunity to share, at least from the Qualcomm side, the upstream journey and the current status of the driver, and what are our upcoming features and plans for this. So I think just to give a little bit of the timeline, I think it all started thanks to Rob, and who added the first KMS driver for Snapdragon. I think if I go by the commit dates, it was back in 2013, and with, of course, some help from Archit on some of the parts. And that time, the chipsets which were added were the APQ 8064, 8084, the 8916, and the 820. And sometime in 2018, we started on the STM845 based Chromebook program, and that's where really we landed the current DPU driver, which we are using even today for adding most of our new chipsets. And this was backed up in probably a year after that with the SC7180 and the 7280 based Chromebook programs, which we added the DisplayPort, EDP, and write-back support that time. And now, thanks to the support of the display team members of Qualcomm, Dmitry, Linaro, Rob, and Collabra, SO Mainline, and other upstream community members, this driver is supporting close to 18 chipsets. And this will keep growing, and it continues to grow at a very rapid pace. So thank you, everyone, for getting us so far. So just to share, so between this 2030 and the Chrome program, why there was a bit of a delayed push from our side is like, it's mainly driven partly because there was a major Android domination of the smartphone market, with all the major SoC vendors going with their own kernels. And obviously that led to the business reasons of us not having really any major Android programs with a pure upstream kernel. This, I think, backed up with really fast commercialization cycles of Android phones, all kind of just contributed to this. And the Chrome program was some sort of really like an inflection point for us to get all this landed, and thanks to like Rob and Sean Paul from the Chrome OS team to help us really land the DPU driver that time. And so why are we doing this now? The obvious question is why the Qualcomm push since last 2-3 years. So first, obviously the first reason is the continued support for all the compute programs which have already commercialized and the upcoming ones. Then the support for new open platforms. This is like an umbrella term we are using for all the IoT programs or the IoT projects or the new XR programs which are coming up with the pure upstream Qualcomm driver. Definitely the Android GKI was a big factor as well, the generic kernel image project of Android, where it was, I guess, according to the stats, it was estimated that the vendor-specific SoC code in the kernel was at one point contributing almost 50% of the product kernel. So I think definitely this project was aimed to keep the ACK or the Android common kernel as clean as possible, and that's why we wanted to upstream probably the framework changes we did, and that work is still going on. And obviously on all of this, since the foundation was built, we wanted to carry on all this good work moving forward. So coming to the current driver strategy that we have, this can be broken down to just these topics from our side. First is definitely to keep enhancing the DPU feature set. This is definitely not easy, and probably when Dmitry comes over, he will cover the feature set, and we'll talk more on this. But we have done a lot of work last 2-3 years on reducing this feature gap between our upstream and downstream kernels, and we are now in a much better shape than we were, and it's only going to improve moving forward. Then the second aspect to this is that we have an MSM bug tracker now to report any bugs from the upstream community. We have a very vibrant community which continuously validates the phones that they have, the devices that they have, and report the bugs back to us. I think they had already been discussing the bugs on the IRC channels, sharing the logs, sharing the images, but having this, the GitLab bug tracker definitely adds more accountability even for the Qualcomm side to fix these bugs. So the discussions can get lost, but the bugs won't. So I think please feel free to open and raise the bugs. We'll try to support them as quickly as possible. Then I think the second thing which we were focusing on was, I think we now have an IGT-based CI in place thanks to Collabora and Rob's efforts. I think we take definitely a lot of care to keep the IGT CI failures in check. We have been contributing quite a bit in the IGT side last couple of years now, and we would definitely keep doing that. We would definitely want to limit those failures. I think thanks to Mark, I think from Google, there is an IGT channel which he started on the IRC for a collaboration between the major vendors to talk about the IGT bugs and features. And so thanks to Petri as well, who has been quite active in reviewing the Qualcomm patches on for IGT. And we have been able to keep enhancing the IGT for the Qualcomm's needs as well. So this will only continue because this definitely provides us not only a good way to keep regressions in check, but also a simple way for us to validate our features for the currently already upstreamed UAPIs. And this has worked pretty well for us in adding some features quite recently as well. And last but certainly not the least, we want to enhance the current DRM CI by adding more boards to it. Just a couple of weeks ago, we added the SM8250 based RB5. This was definitely a new experience for us to add a new board, and we'll definitely use that to keep adding new ones to extend the coverage of the CI even more. So I think now I'll hand it over to Rob to cover the graphics update and also share a little bit on the CI, and then followed by Dmitry.
All right, thanks. Let's see here. All right, so just a quick status on the GPU side of things. These days we have about approximately 30 models of Adreno GPU supported, dating back to Adreno 200. And that's including Adreno 730 and 740, which are landing in 6.7. We've been using for a long time dev core dump for capturing GPU state when there's a GPU hang. And that's integrated in, for example, Chrome OS crash telemetry. And that's been very useful for catching and tracking down and debugging long tail issues, like the issue where the device crashes every like 40 or 80 hours of use. That's kind of something that's difficult to reproduce in person, but getting some information about the crashes has been pretty useful. We're using these days DRM GPU scheduler for job scheduling, and we do, I think, well, at least until Dmitry's Shermem eviction patches land, we're the only ARM driver that supports full gem eviction. And the reason that's important is that Chrome OS tends to make inexpensive devices which don't necessarily have a lot of RAM, and Chrome OS leans pretty heavily on ZRAM swap to make that work. So you have a 4 GB device with 20 tabs open. You might have just only a small fraction of your gem objects resident in memory at any time. So recent work has included user space IOV allocation, which was originally motivated by the Vert GPU native context, because it allows the user mode driver and the guest to not have to wait for a response from the host on buffer allocation. But more recently, it's used by Turnip as well in the non-VM case. So recently, I've been working on, partially in DRM and a little bit outside of DRM, dealing with all of the runtime PM and PMQoS issues with lockdep in the fence signaling path, mainly locking interactions that runtime PM or PMQoS have with FS reclaim, and untangling those with the goal of eventually enabling the fence signaling annotation, so we can be confident that we're not introducing new potential sources of deadlock against the shrinker. And then there's been some recent octal overhead optimizations. So upcoming work, one thing I'm interested in is a user pointer with potentially a slight twist of not necessarily being virtually contiguous in user space. What that would let us do eventually is allocate memory with guest pages. So one of it is kind of expensive when you're running in a VM to map new memory into the guest. If we could allocate gem objects with existing guest pages, that would make that much faster. The problem is, unless the guest pages are physically contiguous from the point of view of the VM, they're not going to be virtually contiguous in the VMM. But if we had a UAPI where we can allocate a user pointer buffer with virtually discontiguous memory, that's no problem to map to GPU virtually contiguous. That would solve that problem. And then the other big one, of course, is VM bind. The interesting thing to solve there is, like I mentioned, Chrome OS leans heavily on eviction. So having something where you have to swap in all of the buffers of a single process would be prohibitive. So would end up meaning we need the existing stuff and the new stuff to coexist side by side, instead of the legacy stuff just being a compatibility layer on the new stuff. So figuring out how to make that work is something I got to work through. So can I get to the next slide? There we go. So on the DRM CI, the DRM has recently been embarking on the GitLab CI adventure. And these days we have a combination of devices in the FD farm in Portland and in Collabora's farm, and now in Qualcomm's farm with the SM8250, which are running kernel CI. So the way we're using this for now is Abhinav, Dmitry, and myself will collect patches from the list and push a GitLab MR, which triggers CI, and targeting either MSM Next or MSM fixes. And this lets us have some confidence that we're not breaking things, especially with so many different platforms out there. So hopefully over time we can add more. So I think off to Dmitry.
Yeah, thank you. So unlike the previous, unlike the hope, I am mostly looking at the display side, not on the graphics side. So yeah, Abhinav started with this part of the talk. We have through display backends in our driver that lets us to support different generations, different Qualcomm chips. The MDP4, the oldest one, that initially started the whole process was done by Rob Clark, and it was done at 3.12, and it supports only the oldest generation. If you have something older, please come to us. We would like to have that hardware. MDP5 has the middle generation. It is now in the maintenance only. It covers the hardware that was on the market until 2017 or 2018. But it is now mostly in maintenance mode, but you can see that there are still platforms being added, and 8226 is one of the eldest platforms that can be supported by this subdriver. So yeah, the growth was was steady. It is now again in mostly maintenance, but if you have older devices, maybe it's now time to take a look at your old Qualcomm phone and start checking what can be done there. Thanks to the work done by Postmarket, by SOMenline, and by other community teams. So that's a great time to take a look. The DPU is the newest driver. It was initially done by Qualcomm. It was incorporated into the kernel thanks to Qualcomm and Chrome OS. And this is where most of the current work goes. There was a slow start for it, but now we have a pretty significant growth. So if the previously time between the platform announcement and actual patches for that platform going in was like, it might be up to years. For the latest platforms, we have a time between platform announcement by Qualcomm and patches going into the mailing list up to 2 months or less than 2 months. And for the next platform, we actually try, and the plan is to post patches and provide support for the new platforms just at the announcement day. So this is kind of a significant change that was possible thanks to Qualcomm, thanks to all the community, etc. So some stats: the MDP5 driver was done par on par by the Qualcomm and by the community. For the DPU driver, there are three major players. It is Qualcomm, it is Linaro, Truly, and the community, which contributed really a third of all the supported platforms by the DPU driver. So again, current features, what we currently do, what we currently plan to do. Of course, DSI, the heart of most of the phones. So we support both normal single-link DSI and bonded DSI, or dual DSI, as you might know it, where two DSI hosts drive the same panel. We now support both command and video panels. So if you had previously issues with your phone and that was the only issue why you did not try upstream, please try and report bugs. We would really like to get all your Qualcomm phones or Qualcomm-based phones to be supported by the upstream. DisplayPort, that was kind of a new stuff in the last several years. And thanks to latest laptops also getting the EDP instead of DSI panels. Yeah, this is one of the main topics now. It is where we currently we have one of our focuses. Qualcomm provided the driver that has 0 failures on the CTS. It passes all the PHY, link, and test pattern test suits. So it is good, it is great, and it is. We are trying to get it to work on most of the platforms. So I was questioned if we can use it on the On the development kits, yes. So for example, the latest development kits work with Linux Next with just a single patch for the display port. So it was not there that way a year ago. Yeah, and of course HDMI, some legacy platforms support HDMI natively, so yeah, that's useful. We have one of the, well, that kind of correlates to the to last talk yesterday. We are heavily using DRAM bridges and DRAM bridge connector in our pipelines. So there is a huge path for the signal to travel, and it is covered by the several bridges. They differ from platform to platform, and for each and every configuration, except the eldest one, except the LVDS, there is a DRAM bridge and DRAM bridge connector. CTM, yep, there is a color management support. For now, we do not support gamma to gamma, but Qualcomm is looking at it, and we are, so both Qualcomm and Linaro is heavily following the upcoming discussions regarding the plane color management and high definition rates images. Write back, yes, Qualcomm added support for the write back, and initially it was done just for 2 platforms for Chrome. Now it is getting supported on most of the platforms where we can do it. So it is a way to easily test. You do not have to resort to CRC, but you can really get the image, check what is there, and I think that will be also important for the HDR. So this is useful. Our platforms have got the EDP PSR support. I think we were one of the first users of the PSR framework, and it was kind of a hard path for us, but it is now done. Please test it. Feel free to use it, and feel free to tell us where we were wrong. So DSC, display stream compression, currently it is supported only on the DSI panels, but we support DSC 1.1, 1.2, depending on the platform, depending on the panel. And I should be proud to say that DRMSM was the driving force behind adding DSC for the panels for the DSI. And of course, last but not least, is the core dump, a dev core dump. So pretty much like the GPU, which can capture the state of the GPU when the hang is detected in the GPU. Display stuff also can capture the dev core on if any of the issues on the times outs or on the display, and then it helps a lot to analyze your logs. So yeah, send the core dumps. That's nice. Yep.
Oh yeah, just to continue with the feature list, I think like Dmitry already mentioned, we definitely are monitoring the color pipeline proposal very closely. I think one of my teammates has already been active on the RFCs posted by AMD and Intel. We participated also in the workshop which happened on day 1. So certainly we will aim to prototype our solution based on the color pipeline RFC which has been posted, and definitely give our feedback and comments to improve it based on our needs. Then the next one is the concurrent write-back support. So to build on the write-back, this concurrent write-back will be used in concurrency with the same primary display pipeline. That's why it's called the concurrent write-back. We will definitely aim to, we have some plans in mind for this as well, so we'll start work on this too. So the DPMST is something we had been thinking of, but just over, the DSC stuff got pushed out earlier than this one. We know, and I personally attended last year's XDC and saw the demos from AMD, and we know that there is a good level of confidence in their Intel and AMD's MST solution. That also gives us a good starting point to start our support, and hopefully we'll get this added soon. The next two are the panels features. So I think Qualcomm has significant expertise with MIPI panels, and thanks to the smartphone market for sure. And then one of the couple of features we are keenly interested in is one is the command mode video mode dynamic switch, because some panels support both modes, and depending on the use case, we would like to be able to switch the modes on the fly. We had been having some discussions on and off on the IRC channels with Linaro on our sync-ups, and we would like to push out some RFC at some point, hopefully soon. And then the next one is the simulation panel framework for DSI panels. So I think for the external displays, such as the DisplayPort HDMI, there is a good Chameleon framework in place to kind of simulate all the monitors by having their edits. But for MIPI panels, we would like to have a simulation framework in place, because it is not possible to have every panel in-house to test it out. And it is both logistically and from the economic point of view, we need to have some kind of simulation in place to be able to validate the DSI call flows and probably even the performance metrics with various types of panel resolutions and the various modes as well, like command mode and video mode and so on. So that's definitely on the list. YUV output over DP is another thing which is should be out shortly. We are definitely planning to get this done very, very soon. We know we have seen some solutions in the upstream in place, so ours will be out soon as well. And last but not the least, the DSC over DP as well. We also have this pretty much complete now. This will also be out on the list probably in the next month or so. So these are certainly some of the things on this list are things you will see on the DRI development list pretty soon. So. This is the features that we are targeting out. One of my colleagues has said a year ago that, it's no longer interesting to bring up new Qualcomm platforms. It is just easy peasy, we can do it in several days or several weeks. Yeah, okay, several weeks, not several days. But on the other hand, it allows us to focus on a more generic and more integration part of the stuff. So 2 years ago on the Linaro Connect, we have introduced the virtual planes, the way for us to try to drive the actual hardware by not tightly binding the hardware backends for scanning the buffer and the DRAM plane for different reasons. And for one of the reasons is that a single hardware block cannot. On some platforms, it cannot support 4K resolution, but the rest of the hardware and the platform itself can support 4K. So that was one of the reasons. And also it allows us to have more versatile configurations. So like having more panels that there are hardware blocks, having less panels less planes that hardware blocks, switching between these modes natively, transparent to user space. The first patches have landed. We got a 4K proper on these platforms, but now we are really trying to get the most that we can get from the hardware by using and reusing the hardware blocks and getting twice as many planes as there are hardware blocks. And this will be completely transparent to user space, so no need to worry. The only thing that if you overcommit, you will get an error from atomic commit, that's all. From atomic check, that's all. DSI, yeah, so it is pretty good. It has been in the kernel for quite a long time, but there was an issue that has been there for as long as there was support for DSI. DSI doesn't fully fit into the DRAM's thought of the states, and it has the third state where the link is already up, but there is no video signal, and there is no place for that in the DRAM framework. There was a solution that was upstreamed last year by Dave Stevenson that introduced this pre-atomic, pre-enable pre-first and prepare pre-first. But yeah, we switched to using those flags. And if you missed the talk yesterday, yeah, they switch the order of the callbacks in the bridge chains. So instead of just going from the end to the encoder and back, they allow you to trick
some of these callbacks and to say, okay, let's enable the DSI host first, and then the panel will be able to send comments. But actually, at some point during this development cycle, we faced a problem. Okay, there is a panel driver, there is a DSI host that they should work together, but neither of them knows if the DSI panel uses this flag, if there is actual, if the panel expects to be powered and at which point. So we are now trying to get this sorted out by explicitly telling, okay, yes, dear DSI host, please switch up, please switch on, please power on the link. We want to send comments. So this is on the mailing list. I would like to hear your comments. Yep, that's it. Display port, yes, as I said, it is already there. It is mostly working, and we are working now on getting to work with the user space, so that user space is notified when there is actually it is a display port or it is a USB-C. What happens? What is the dongle that is connected? Which port corresponds to which? Which Type-C port corresponds to which display port, etc. So there was the patch that was landed thanks to Intel. There are several problems with it, so we are looking and working on getting the user space API in a more sane state. Last but not least, we are also working on blending improvements, so like getting more planes, using less bandwidth, thanks to precious hardware features by only Qualcomm chips. So that's it. Some stats. There we have a large amount of contributors through the whole history. We have, I've listed largest contributing parties. Of course, it is topped by Qualcomm, but it still has other parties. So for some of them, it is just patches because one of the maintainers or one of the guys was fixing or redoing stuff. We would like to point out to some in line that is the community project done in the spare time by poor guys that have Sony phones and rich guys that have Sony phones, and they work a lot on getting them up and running with upstream. So that's great. Other than that, yeah, that's it. So I will not name the names. You see them, and some of them are pretty much known. So, yep, that's it. Okay, it seems there are no questions, so thank you for listening. And again, if you have a Qualcomm phone, Qualcomm phablet, yeah, please give it a try with the upstream. Most likely, we can get it either to work, or either it will work, or we can get it to work pretty easily. Or if not, that will be very interesting for us to lay our hands or to lay our minds on that platform. So thank you.
Thank you so much.
Before going to the coffee break, we found some items during these days. So if you missed something, just let me know and see if it's one of those. So yeah, I found yesterday, I think what was a laptop charger. There was a green cap for somebody who was on the floor on Tuesday, I think. So yeah, if you missed something, just let us know. Thank you.
I'm ready, Ado. Okay. So, hello everybody. For the last 2 years, I gave a talk about the state of the etnaviv graphics stack, and I'm happy to continue doing so today. I will cover different topics today, from CI to Glass 3, and I will talk a little bit about some legacy love. But before we dive deep into the topic, let's talk briefly about me. I've been working on etnaviv for many years now, and in the early days I mostly was interested how a GPU works, what the components are used, and how the big picture looked like. For a long time it was just another hobby for me, and I did some small contractor work that I lovely called my etnaviv days. But visually, as you can see, the old color theme from my old presentation has changed. It's not that black and white theme anymore, and that's for a reason. I started doing contractoring work for Igalia full-time for the past five months now, and I'm really happy to get the opportunity to work in the open source graphics stack. So, enough about me. For preparation for this talk, I basically looked at what happened in the different Git repositories. And let's start with the kernel driver. I think the last year was more or less in quite area of work in the kernel area. But the biggest feature that happened was the support for NPUs done by Tomeu. As the NPUs share a lot of similarities to normal Vivante GPUs regarding the DMA fetch engine and its command stream, it just needed a handful lines of code to support them. Also, all the reverse engineering tools we used for the GPUs are supported there. The other new big parts that happened in kernel land were the addition of new hardware database entries for new supported GPUs and NPUs. Such hardware database entry provides information about supported features and limits about a specific GPU, and that will be consumed by the user space. And overall, there were some small fixes and improvements in kernel land. On the Mesa side of things, a little bit more happened in the GPU stack. Lukas Dach from Pengotronics and I were working to fully support and enable MSAA. There are still some little problems, and that's why it's behind an opt-in feature flag. The same is for this tile buffer sharing thing Lukas is working on. There are still some problems, and it's also behind opt-in feature. The etnaviv Gallium driver supports or gain support for performance warnings. For instance, you will get such a warning if there's a shader variant that gets compiled during draw time, or if an application uses conditional rendering that is implemented onto CPU, as there is no hardware support for this feature. The last month, I was working on different compiler linker topics. For instance, we support negative inline immediates now. Our own near lowerings got better and helped to decrease the instruction count. And I finally was able to tackle an item that was sitting for too long on my to-do list. Piccoli's GLSL routing tests are now passing, which is really great. With all the time I have now to work on etnaviv, I was also able to tackle some cleanups in the base of the Gallium driver. Example, by removing some hand-rolled conversion helpers, which is a nice step towards more cleanups that will be coming later. And also, we were able to fix a lot of crashes in CTS and also fix a lot of fails. The next topic I will cover quite quickly is CI. I'm a very big supporter of unit testing and continuous integration, as it makes the life of the developer much easier and helps to prevent regressions. If I need to describe the etnaviv CI at the moment, I would say it has proven its value. it forced other developers to take care of etnaviv and don't break it. My board farm is still bare metal based, and it costs 0 maintenance for me. It just runs. But to be fair, my board farm is still running in this manual mode where you need to explicit press a button in GitLab that your job, your merge request gets run on etnaviv CI. But I hope that this will change soon too. But the board farm is used in the nightly CI runs that are happening in Mesaland. My board farm currently consists of 12 devices ready for use. So they are fully connected and can be used right now. As you can see, I have mainly GPUs, different GPUs under test, and mainly GC 2000, 3000, 7000 based GPUs from, only a handful of these devices are registered as public runners. This has mainly 2 reasons. I wanted to do more work on the Gallium side than CI for the moment, and I waited for this CI-tron thing to happen so that I can evaluate it and hopefully can convert from bare metal to CI-tron in the next month. There's one thing that I'm really happy about is that the community wants to provide own board farms for CI testing. For instance, David wants to provide some Librem 5 dev boards. Sam wants to provide some GC880-based board farm. And also at Igalia's headquarters, there will be coming a board farm specific for etnaviv needs. So these are really, really exciting news, and I can't wait to see all the board farms hooked up in free Desktop's GitLab CI infrastructure. And if you're interested in running your own board farm, just say hi to me and we can talk about it, because there are different more models supported by the etnaviv driver than just this handful provided here. So, my personal goal for the last 2 to 3 months was to get Glass 3 working fully conformant on etnaviv on a GC7000L-based GPU. I spent a lot of time reverse engineering, verifying new shader instructions that get used for the job, try to understand the differences between the different GPU models, and got really, really far. I have only some lowerings that I need to do for fragment shaders that are not yet fully done yet, but else it looks really, really nice. I'm able to support multiple render targets, 4 or 8, depending on the GPU model. The merge request for this is not yet done, as the Gallium drive at the moment is written only with 1 render target in mind, and it takes a little bit of refactoring to nicely integrate it, the multi-render target support. So everything looked fine, but then bigger near refactoring was happening, and it caused a lot of problems, and I had to shift my focus to looking more into this near refactoring thing than into Glass 3 stuff. In theory, it should be quite easy to use the new legacy helpers, and the job should be done in 1 or 2 days. But sadly, the current backing compiler had a different opinion than me, and so I spent really some days to get it working. By working, I mean ShaderDB looks okayish, and CTS tests are okay too. But as you can see here, my first attempt wasn't that great. So I need to go back to the drawing board. I came up with a nice solution, but I had to clone existing render near paths that is not existing in the tree anymore. I did the whole source modifier thing now on my own, and it took me about a week to get to this point, and ShaderDB is now much better. So, but I got feedback from the community that the compiler backend isn't that nice. And the weakest point is really the current backend compiler. We do a lot of tricks. We do near constant value pollution, I call it. We misuse the upper 32 bits. And this has the side effect that near validation doesn't work. We have a lot of areas where we in blind flight mode late in the compiling process. So we need to add manually some near print shader calls to see really what is the last near shader you are seeing. And the current assembler is not aware of different instructions encodings. So you see a lot of funny source code like this where you need to set some texture bits and bytes to get, for instance, here the load instruction. And it feels and looks really strange to me. And the biggest pain point, we have miscompilations. I've been working on some shader-based emulations, and they are working on different GPUs, but not in etnaviv, because the compiler miscompiles it. And also I had to spend quite some time to work around how the compiler is written. There are near lowerings, not in a pass, but shared across the source code, which is really hard to work with. So I'm really proud to tell you that I've been working on a new backend compiler called the etnaviv backend compiler. There are quite some trends in compiler land right now, and I will be honest with you. Not a single line of Rust, no SSA-based register allocator because of the nature that the instruction set architecture is. I use a lot of EtherSpec magic to do the job. I use the old register allocator. And finally, we have a backend IR with own optimization passes. We are supporting control flow, different bit sizes. And as a test bed, I used OpenCL. But I'm a lazy guy. So I looked around in the tree, fell in love with Asai's compiler, basically copied everything over, renamed stuff, and added the needed VEC4 sugar on top of it. As I told you, I was using OpenCL support to test bed this based on the work collaborated. And so let's have a look at the really simple OpenCL shader. Nothing too fancy, a simple rotate. And here we can see the backend IR after copy propagation, that code elimination and liveness analysis. And it really looks lovely, what I say. And I even made it possible to annotate source registers, like here the base address or the offset, in EtherSpec. So in the XML file is really where everything is lying. And here we can see the final assembly, and it passes the Piccoli test. All the EtherSpec changes needed for EBC are merged already, and EBC will come later this year. So now a quick talk about legacy love. The etnaviv GPU stack will bring new features to all the GPU models with the help of shader magic. The etnaviv supports many GPUs with different supported features, and the binary blob does some legacy tricks in the shader, and so does etnaviv. And the plan is to make more use of these shader emulations, for instance, to emulate logic ops and do own lowering specific to etnaviv, like border color lowering. From time to time, etnaviv feels a little bit dead, but I think that these times are now changing. And now it is time for some questions.
So you mentioned that you are looking into border color lowering. Is this meant to be conformant for GLES 3.1 border color in support, or is this just a good enough to be better off for the big GL, which wasn't conformant in the first place? And the reason I ask is that the obvious way to do border colors that's everybody's first attempt is not conformant as far as I know, and doing it conformant is very expensive and probably not worth it for the legacy hardware you had in mind. So.
Yeah, the initial goal is to get it running somehow. So conformance is not the main goal for this one. Okay, if there aren't any questions, I would say thank you.
Danilo? Danilo, do you hear us, Danilo? Danilo?
Yes. Do you hear me?
Yeah, perfectly.
Yeah, great.
Okay, perfect. We have 5 minutes left yet.
Mm-hmm.
We will play the video here.
Mm-hmm.
And then, yeah, we are all set for the Q&A.
Okay, okay.
Okay, so Danilo's talk is about to start. It's going to be a pre-recorded video, but he is online for the QA session. So go ahead.
Hi. 2 years ago, I gave a talk on how to use RenderDoc to debug your driver. This time around, I'm going lower level and want to talk about the tooling I made for Turnip driver, which help us debug various issues. I believe that most of it may be useful for other drivers as well. In addition, I will give a short overview of other tooling which helps accomplish similar goals, but for other drivers. But before, briefly about me. I took a part in developing 2 mobile games, and while I did not work much on rendering back then, I still saw quite a bit of fun driver issues. Afterwards, I accidentally started working on Mesa and debugged all kinds of issues in various games and applications since then. Now I've been working with Igalia for 3 years, and presently in the process of upbringing the new Adreno GPU generation in Turnip. Let's start by stating the problem. After you debugged a nasty GPU issue, half of the times you think, what if I was able to quickly edit the GPU packet? Or what if I was able to dump this buffer's memory here? Or it would have been nice to print that shader register. And every time you think, I will implement it later, and then forget about it until the next nasty bug. Last time though, it was not just a bug needed to be fixed, but a new generation of GPUs needed to be supported in the near future. Maybe you know that there is no documentation for Adreno GPUs, and all the information is reverse engineered. So there is a lot of what does this bit do kind of testing. This finally tipped the scales and the tooling was implemented. Though afterwards I believe that it is worthy regardless of having the GPU documentation. For now, I will talk about the tooling I implemented in Turnip. Just keep in mind that I may omit or miss some edge cases, since the point of it is to ease the debugging process in the common cases. Afterwards, I will talk about what other drivers have. Now, let's start from how we could improve the debugging of unrecoverable hangs. For recoverable hangs, there is, for example, graphics flight recorder, which uses breadcrumbs at API level and gives a probable range of calls where hang occurred. Or you just could go through draw calls and find the ones which hangs. With unrecoverable hangs, you have to reboot the system each time. In such case, graphics flight recorder is useless, and going through draw calls in RenderDoc is either not possible or too slow with all the reboots. And such unrecoverable hangs are not that rare occasion for us. The issue with graphics flight recorder is that it writes results to the disk, and what's written is far behind of what's happening on the GPU. One of the solutions would be to modify GFR to have synchronous mode, where GPU will not race ahead of the CPU and breadcrumb status would be sent over the network. Unfortunately, this would require at least one more Vulkan extension and more work on GFR. With another downside being that GFR works on API level, while in reality one Vulkan call may not strictly correspond to a single GPU command. In example, begin render pass may internally use a lot of different 2D and 3D bleeds to clear and load attachments. What do we know about unrecoverable hangs that we should take into account? Luckily, at least from my experience, unrecoverable hangs are rarely caused by synchronization issues. So no matter how heavy-handed synchronization we would need, it likely will not affect the result. On the other hand, if we allow GPU to race ahead of the last known to the developer breadcrumb, even by a few commands, the usability would be drastically reduced. Another issue, even if we perfectly synchronize GPU execution with logging, some hangs happen asynchronously to the GPU packet that triggers them. Fun! A packet may submit some work to another GPU unit, and that unit may hang later on and bring down the whole GPU. It also could be impossible to properly wait for this unit to complete. So the current solution in Turnip is breadcrumbs are inserted after each GPU command, which has a chance to hang. GPU writes a breadcrumb and immediately waits for this value to be acknowledged on the CPU side. CPU in a busy loop checks the breadcrumb value. If new one is found, it is sent over the network. Only then the CPU acts the breadcrumb and GPU continues its execution. Here is a simple visualization of how it works. Surprisingly, it worked not as slow as I would have thought. Okay, what about asynchronous hangs I talked earlier? We have a simple way to deal with them. We require explicit input in TTY for each breadcrumb. Or we could add a configurable delay between them, which I probably should implement instead. Anyway, works well enough. Here is how it looks like in practice for Turnip. First we increase GPU hang timeout. Breadcrumbs could easily trip it. On another machine we receive the breadcrumbs via this nice script. Then we set where the breadcrumbs would be sent over the network, set the first breadcrumb to require explicit acts from TTY, kind of a breakpoint. Then we launch the workload and wait until the hang. Now that we have the last breadcrumb value, we reboot the testing machine and relaunch the workload with breakpoint just before the last breadcrumb. Then we manually add breadcrumbs until we have a hang. Here are the links to my blog post about breadcrumbs implementation in Turnip and merge request which implemented them, if anyone is interested. Now we will discuss what to do when you found something with breadcrumbs or when they are not helpful at all. Breadcrumbs are good for finding a command that hangs, but they cannot tell which part of the GPU state caused it, and they are useless for misrenderings. Some issues are not reproducible with breadcrumbs enabled, or just have low reproducibility rate. Let's address the reproducibility rate first. For reproducibility, a simple solution is to be able to capture and replay the command stream which causes the issue. Capturing already exists for the most drivers. Just keep in mind that you'd need to capture all the buffers. With this, it is trivial to replay the submissions back. While replaying is simple, ideally it requires user space GPU addresses. Without kernel support for them, replaying is still doable. You just allocate a lot of memory upfront and do allocations from it. Being able to replay submissions is useful to confirm that the issue is not a fluke, but not that useful to find out the cause. What are the caveats? I think that one big caveat we didn't have to handle in Turnip are multiple queues. When we replay back the command stream, we re-upload all of the memory at each submission, which obviously doesn't work if workload is being submitted to several queues and is able to run simultaneously. Though it shouldn't matter for most cases, and a single queue could be forced. Next issue is that submission recordings with all the GPU memory could be impractically large, especially if we want to ask user to provide the one. There are also possible issues with timeline semaphores and probably something else less expected. Anyway, most of the issues happen where all of this doesn't matter. At least they did not matter in the most cases I debugged. While it's useful, it doesn't help that much on its own. The obvious next step is the ability to edit the command stream before replaying it. It is surprisingly easy to implement the editing in a minimal way. And even in this form, editing is extremely useful. Comments are emitted in a raw form, and their decoded representation is in the comments, quick and dirty. If you are going to implement it, you'd get bonus points if you could emit proper register definition without any values. You also would want to edit shaders in the command stream. Most drivers already have a way to edit GPU shader assembly in order to support the debug option to substitute the shader assembly. So it should be simple to support for command stream editing. It also may be a good idea to represent not properly decoded instructions with their raw binary form, to not alter the execution. Now that we are able to edit the command stream, how it is integrated into replay tool. The decompiler emits C code with raw commands. The compiled from it program could emit GPU command stream with any base address. The replay tool takes original command stream capture, finds unused memory range, and emits edited command stream there. When replay encounters a target submission, it overrides the submitted command stream. Works like a charm. The only limitation may be self-modifying command streams. With being able to edit the command stream, the next simple but incredibly useful step is to add helpers to dump contents of GPU memory and shader registers. Printing GPU memory in command stream is easy, but the naive approach I have implemented is not perfect. If you do a memcpy equivalent in the command stream, it would require at least one cache flash, which may change the memory copied from the memory GPU would have actually seen. Probably a proper way to handle this would be to hide GPU execution from kernel and dump the memory from there. But I haven't looked too much into it. Printing shader registers is just a bit harder. It would require incrementing global offset and writing the target register at that offset. Simple while being extremely useful. You don't need a full-blown printf or GDB for shader debugging to gain their main benefits. Especially it's useful for reverse engineering the GPU, because now it's easy to see what proprietary driver is doing in its shaders. Trying to make that print interface nicer would immediately run into many issues. Want to not manually specify temporary registers? It would be much harder to allocate them at this stage. Too much trouble for a little gain. That's all features we have. So a short summary. A tool to replay command stream submissions, a tool to decompile a command stream into C code, an option to replay edited command stream, helpers to dump GPU memory from the command stream, helpers to dump shader registers. Altogether, they form a powerful debug tool. Now let's move to another issue and the tool to solve it. One of the usual causes of the weird hangs and misrenderings are stale values in the GPU registers. They may appear as a random geometry flicker, or game hanging at a random moment, or a rare CTS test failure. I implemented a simple and in many cases effective way to debug it. It's not perfect, but catches more than enough issues. The solution is to write invalid values to all known registers at every possible point, and hope that if such invalid value is used, there would be a visible effect like corruption or even GPU fault. In our case, stomping registers at the start of command buffer, before each render pass and bleed, proved to be good enough. If failure is found, it's easy to bisect for the offending register. It is far from a silver bullet. There are a number of limitations one should be aware of. It could be a bit tricky if it is a combination of registers that causes the issue, and not a single register in isolation. Also, Vulkan pipelines could be set outside of render path. Though the setting of pipeline far away from the place it is used doesn't happen in real-world applications. Another limitation is that register stomping doesn't help if stale registers are between draw calls. And the final one is that default invalid value may be valid for some registers. Okay, how it looks in practice for turnip. We mark each register with where it is used. In turnip, we divided it into two categories. The ones used outside the render passes and bleeds, and the ones that are used inside of them. To stomp register, you need to specify the range of registers to stomp, which is necessary for bisection, and which register categories to stomp. Then you launch the application with these options and look out for any failures. We also use it in CI on a fractional CTS run. That's all of the turnip tooling I wanted to talk about. To summarize, we have driver breadcrumbs, command stream replaying and editing, which includes GPU memory dumping and shader register dumping, and we have a debug option to find stale registers usage. Now let's talk about other tooling which helps with similar issues I talked about. As for the generic tooling, there is not much of it. There is only graphics flight recorder, which is a Vulkan layer which instruments command buffers with completion tags. It requires AMD buffer marker extension, but anyone could implement it easily. As for not so generic tooling, there is some tooling available in VKD3D Proton to help with debugging its issues. It has breadcrumbs, shader printfs, and descriptor debugging. What about Mesa itself? Most Mesa drivers have some features to somewhat assist in GPU debugging. There are many feature toggles and debug flags which help narrowing down the issues. Most drivers have a debug option to replace shaders with custom shader assembly. That is useful to debug hangs and faults in the shaders. Aside from that, there are tools to record GPU submissions and GPU crash dumps. That's all for Mesa's tooling. Now there is a really cool tool for Radeon GPU debugging on Linux, called UMR. With it, one could read and write GPU registers, dump the state of all running shader waves. In case of crashes, it's possible to get an approximate location of the crash in the shader. So it seems to be a truly useful tool for debugging. There is a blog post by Meister where he uses it to debug a GPU hang in Street Fighter 6 running through VKD3D Proton. Probably the most powerful tool we may have would be a proper step-by-step shader debugger. A great job was done not so long ago by Marcel Kies to make a prototype that shows that step-by-step debugging works. This is possible because Radeon GPUs has some machinery for shader debugging. A trap could be manually set in a shader or by other means. When it is reached, a special trap handler shader is executed. This shader has additional registers available to it, and it has higher privileges than the ordinary shader. Then the communication with CPU side of the debugger is done via uncached BIOS. All of this is enough to implement step-by-step debugger for shaders. I hope this work would be upstreamed in the future. For now, you should read a lot more about it in the blog posts by Marcel Kies himself. That's all for open source solutions. Now, what about the proprietary ones? I don't know much about them, to be honest, and most of the work in debugging space is seemingly done for compute applications and not for the graphics ones. For AMD, there is a Radeon GPU detective. It offers a post-mortem analysis of GPU crash dumps, detailed information about page faults, and breadcrumbs, which looks similar to what Graphics Flight Recorder offers. I have not seen more advanced features there yet. Now, for NVIDIA, there is NVIDIA Insight Aftermath, which builds upon NVIDIA Insight. It makes possible to collect GPU mini-dumps, collect breadcrumbs, visualize GPU state at the moment of the crash, and show crashing shader and its registers. That's almost all what you want from shader crash debugger, aside from step-by-step debugging, of course. That's all the tools I know. So now it's time for questions. Maybe I haven't mentioned some important tool, maybe you have an idea for a new tool to implement. Ask away.
Okay, that's the time for questions now. I think he's hearing us. Danilo, do you hear us? Okay,
I'm
perfect.
hearing you. Yes.
Okay.
Right.
Any question?
Hi, one of the issues we've often faced with breadcrumbs on the AMD side is that when you debug games, like you don't always hang at exactly the same breadcrumb because, of course, things are dynamic. The memory dumping is a really cool feature, but I've always thought like, hey, you need to do that before the hanging command if you want to replay the hanging command. So like, in the capturing, do you have any tricks to deal with this?
So what you are saying is that if we capture the memory right after the hang, like we cannot replay it back to get the hang.
Right. So like, where do you capture it, and like, how are there any tricks to know like when you shoot?
Yes, you are right. Half right, probably, because we could capture the memory right after the hang, and rather a lot of hangs do reproduce, even if in such cases. So it's not important for all the cases, but it's something that one should keep in mind, that the memory may be not valid for replaying. That's true. Alternatively, you could capture like from the start, the memory starting from the application start, but the space requirement would be huge. Yeah, that's one of the limitations of this method.
Okay, thank you for the insight.
Any other question? Okay, that's all. Thank you so much, Danilo.
Thanks, everyone.
Hello, everyone. My name is Michael, and I will be talking about Wayland shells for embedded systems. First, about me. You know already my name. I work as an embedded Linux developer at Pengutronics in Germany, and I am part of the graphics team, and that's why I'm also here. At Pengutronics, we work with embedded systems. So what are the embedded systems I'm talking about? These are digital signage. That means the large screens you see everywhere nowadays where you get some information. Automotive infotainment systems. I put the automotive in braces because you have them on different places like planes or whatever. Industrial control panels, like you have big machines and they have some display which interacts with the machines, allows you to control it, allows you to monitor the machine. And to a certain degree, game consoles and VR systems, because they kind of have similar requirements as the other systems. And I saw a lot of them here, and I guess a lot of you are interested in them, so I just put it on the list. So what's the difference between an embedded system and a desktop system? First, you have a lot of resource constraints. They are less nowadays, but still you have to really use hardware accelerators there and watch for memory bandwidth usage. So that's really constraints that you have to deal with in embedded. You have custom input devices. Nowadays, often there is a touch screen, but you also have like custom physical controllers, which are different than what you expect on a desktop system. And usually the user interface that you're interacting with is defined by the system developer. So on a desktop system, you have your desktop with windows, and as a user, you expect to move the windows around and be responsible for placing the windows. On an embedded system, you usually don't want the user to move the windows around, but you as a system developer and designer want to make sure that the window layout is exactly as you want. And this talk focuses on the last point, on how to manage the windows in an embedded system. Common UI layouts in embedded system are just a single full screen application. You run one application, it takes the entire screen, and it shows you there. So not much to do with window management. Sometimes you have systems with multiple outputs, like the front and the back of a screen, or next to each other, or a small screen and a big screen. And you run one application per output. That's also a common setup. Maybe you have two applications and you want them next to each other on the same display. Or you want to have a picture-in-picture that you have one big application covering the entire screen and some video stream or whatever just covering part of the screen. That's also very common for like having a camera streaming into part of your display. Or you have something more complex, like some certain fixed setup where you have multiple applications on certain places on the display, or even more device-specific behavior that moves the windows around when a new application appears or disappears, so it changes the display, the window layout depending on the applications that are running. In Wayland, the window management is done by the compositor. That's different to X. We heard a lot about this. This is one thing that we have here. And usually the layout is done by the shell. So that's something that's implemented into the compositors. If the system developer needs control over the window management, the system developer has to deal with the compositor. Let's look at different compositors that are out there for covering the use cases that we saw before. In Western, we have the kiosk shell, which is a single full screen application per output. So that's really suited for this very common use case of one application. You just fire up Western with a desktop shell, fire up your application, it will be shown full screen, done. It also works with multiple outputs. You can specify in the config which application is shown on which output. The applications are identified via app IDs, so you have a certain degree of control or are able to identify your application and do whatever you want to do with that. And the Wayland clients can use the XDG shell protocol, so that's basically implemented by all of them. So clients just work. A bit more about the app IDs. They are part of the XDG shell protocol. They identify a general class of applications. And the specification explicitly states that these can be used by a compositor to group the windows and know where to place them. The problem is a bit that it's a group of applications, so if you have multiple applications running, they will have the same app ID, even if they may behave differently. Then to a different shell, the IVI shell. It is for in-vehicle infotainment, so it's specifically designed for an embedded use case. It's implemented it provides the possibility to add plugins to Western and to add the custom behavior via these plugins. And it has an API for these plugins that can be used to customize the layout. So have multiple layers, have different surfaces on these layers, and position them explicitly. So this is very useful for the case where you want to place your window on the screen with your own code. It also has a client protocol that Wayland clients can speak, where there is some mechanism to identify the applications, but I haven't seen that much applications actually implementing this Wayland client, this IVI Wayland client protocol. And one thing that's in the IVI shell is that it's a surprisingly large code base, so it has different parts that are running in Western, loaded as a plugin, and there is even a user space application or a user application that interacts with the plugin. So this is surprisingly large, and if you just need some mechanism to control the windows, you won't use most of that. Then there is the AGL compositor, which is coming off from the automotive-grade Linux. It's also an embedded use case. It's kind of a next step over the IVI application, or a replacement for that. It uses the AGL shell protocol, which for the clients to allow a certain kind of degree. It's different from the IVI shell application protocol, but still clients have to implement it to have a full control over or make use of the AGL shell. Identification also happens via the app IDs of the XDG shell protocol. So that's with the same benefits and disadvantages of the app IDs. It also assumes that your desktop will have like a panel and a background, so there are certain assumptions built into the AGL shell about your window layer or how your display will look like. And it uses not a plugin mechanism, but it uses libwestern. So it replaces parts of Western, which is, I'm not sure because you, if this is a good solution, because you lose certain bug fixes and feature improvements that happen in Western in the front end, and you need to port them to the AGL shell. Or if you use a similar mechanism, you have to port the improvements as well. Then there is not only Western, but WL roots. If you search for kiosk shells based on WL roots, the first thing that comes up is Cage, which is a single application full screen use case. Some interesting thing that occurred to me is if you have multiple outputs, it will just scale the single application across all the outputs, which is in most embedded cases not something that you want to have. Because you have a single application, you don't need to identify your clients. And as said, it's built on WL roots. Then there is a GameScope, which is for a single application full screen using X11 applications. It's optimized for zero copy using libliftoff, which you usually also want in your embedded application for making use of the DRM planes. It has color management support. You also usually want that in your embedded system. It doesn't need client identification. It's built on WL roots, but it's kind of out of scope for this talk because you don't have window management on GameScope because it's single application. Then there is FOC and FOSH, the shell for the Librem 5 phone. I put that there because it's also phones are kind of similar to embedded system, just a bit more powered. And what I found interesting there is that the compositor and the shell run in different processes. So the thing that you modify for getting your custom behavior there is not the same process as the compositor. So if you crash in your UI thingies, your compositor may not be or is probably not affected by that. So you have some kind of separation between the compositor and the shell. Another compositor is the Qt compositor, which allows you to use QML for your window management. So this is taking toolkit mechanisms to design your applications and applying it to compositors to move windows around in a really easy and descriptive manner where you just put your coordinates for your windows and allow you to easily manage the desktop. You have the Wayland protocol exposed into QML, so you kind of start to implement a whole compositor in QML if you use the Qt compositor. Then there is an open issue in the Western GitLab for scriptable window management, which looks interesting as adding a scripting language, in this case Lua, to Western to allow a certain degrees to manage surfaces in Western with your own code that you provide as a system developer and not rely on the user. Then I have several questions that I'm asking myself, how to use shells in embedded systems. So regarding custom window management, are the hooks for the surfaces in this script enough, or do we need something more like an API or something in the window shell, in the IVI shell? And do we want to separate our custom code from the compositor code or keep this together? For client application identification, are the app IDs sufficient? What about the same application that runs multiple times? This is, for example, relevant for GStreamer. If you run multiple GStreamer pipelines, they will, I'm not sure if they set the app ID at all. So that's a problem. And do we need or want a protocol for clients to identify against the compositor? Do we need something special here in embedded? Is there something missing in the XDG shell, or can we just rely on it? And we need support in the graphic toolkits for that. There are some further concerns for embedded systems. I won't go into them. And with that, I'd like to thank you for your attention. And I have a lot of questions. If you have answers, remarks, different opinions, or other questions, come to me, talk to me, and ask them. Thank you.
Hello, thanks for the talk. I just want to point out that for GameScope, we do have window management. So there, by default, the mode that you describe is correct. Like single application, we just display it. We have a managed mode, which is what we use on Steam Deck, where you can tag applications by ID. And then there's a programmatic interface you can use to switch between apps, switch between windows. So it's not, there's not like a window decoration or something you can drag windows around. It's more for something else to act as a shell or some scriptable thing. We can extend that to, we already have pop-up windows and a bunch of different things that, that fit our use case, but I think it could easily be extended to support arbitrary position and kind of an arbitrary scene graph or anything like that, if that would be helpful for you. I don't think it'd be a giant change. So okay. We should chat more, I guess.
Okay, thank you.
Yep.
Yeah, hi. Thanks for the presentation. I just want to point out that in Cage there is an option to change the behavior of full screen window, so it doesn't have to occupy the whole monitor space. There's a command line option you can change the behavior of that to be per screen. And I maintain Cage, so if you have any questions, feel free to ask. In terms of client identification, one option would be to use security context protocol. We have recently standardized with the instance ID. You can basically wrap an existing Wayland client without modifying it and attach some more metadata, like an instance ID and custom app ID or something. So maybe there's a solution there.
It's the session or security? I didn't catch the...
The name of the protocol is security context. It's designed to be used by Flatpak and other sandboxing stuff to be able to reliably identify, this Wayland client is running in this Flatpak sandbox, and without any kind of PID races and unreliable hacks to get back this information. But it could be used, I think, for more precise client identification as well.
Okay.
Yeah, maybe an option.
Okay, thank you.
Hi, thanks for your talk. One thing that I was missing is also GNOME Kiosk, which is basically, it's based on Mutter, but without all the bells and whistles around GNOME Shell. And so it's specifically meant for kiosk things. And it also has this kind of scriptability issue. So I wonder if that's also something that would be interesting to collaborate on at some point. Because I think that would be cool to have, really. Yep. I think we miss something really here in the Wayland world. So yeah, thanks.
Thank you. I don't see any more hands. So 3, 2, 1. Thank you again, and have a nice lunch.
Okay, so nice, 1, 2, 3. Yeah. How's the volume? Okay? Okay. All right, so thank you for being here. Sorry for taking you away from lunch at this point. I hope you're all awake and attentive at this point. And I do hope this presentation acts like a small dessert for you. So this presentation is about the story of the Wayland driver for wine and some of the challenges we have faced and are still facing. All right, so I assume that most people in this audience at least know what Wayland is and what wine is, but perhaps some of you may not know exactly what the wine driver is. So a wine driver is the component that helps wine integrate with the native Windows system. It does the mapping between the two worlds of Win32 and whatever the native system is in terms of input, output, window management, events. And WineX11 is at the top because it's the oldest and most mature. And it enables Wine to integrate with an X server that's either a traditional X server, as we have known it for years and years, or these days with X Wayland, which then can talk to a Wayland compositor. And this presentation is about a new driver that allows Wine to directly interact with the Wayland compositor without needing X11 in between, X Wayland in between. So one thing I think that is clear at this point is that the first path, the traditional WineX11 to X server, is becoming less and less relevant as time goes by. And I don't think it's going to be an important consideration like in the long term. But of course, we still have X Wayland, and so we do have at this point a path from Wine to the Wayland compositor. And of course, the question is, why do we even want a Wayland driver since we already have some kind of solution? So, like the big picture here is that the fundamental vision is that we want to move towards a future that doesn't include X11. X11 had a good run, but it was designed for a different world. It makes different assumptions about how applications should behave and also is built on different security considerations. So at this point in time, I think for many people, Wine may be one of the few remaining pieces on their system that requires X11, even in the form of X Wayland. And it's not inconceivable that going forward, at some point, X11 will effectively become like some kind of de facto Wayland protocol for Wine. And I mean, it's a really heavyweight protocol. I mean, probably we can do better than that. Okay, so that's the big picture. What about some more concrete concerns we have about X Wayland? So first of all, X Wayland requires integration with a compositor, and that has both an initial cost, but perhaps more importantly, it does have an ongoing complexity and maintenance cost. And that's maintenance both in terms of code, but also in terms of ensuring that X Wayland and all that it requires, like in terms of window management, continues to play well with all the features and the policies that the compositor may want to have. So furthermore, the path through X Wayland requires a double API translation, so from Win32 to X11 and then X11 to Wayland, which although may be good enough, like each step on its own may be good enough, it's still not lossless. So we do have the problem of introducing more bugs or more mismatches along the way. Also, Wayland is another layer in our stack, and all kinds of information, events, buffers flow through that. And as with most layers, it's not unreasonable to assume that at some point that it adds some overhead and affects performance, latency, etc. So we would like to remove that layer from our stack. And last but not least, since Wayland, I think everyone, at least here, agrees is the future and actually the present of display systems on Linux and other Unix systems possibly, it's where all the interesting new features and innovations will happen. So it's unlikely that X level will see counterparts to many of these innovations. And a good example of this is probably color management and HDR, which is being developed in a very full form and very capable form at this point for Wayland. All right, so hopefully everyone has been convinced now that we need a Wayland driver. But yeah, so how did the journey begin? So with all that in mind and with that lofty goal, a couple of years ago, we started on this journey to explore the viability of such a driver. So remember, this was, and still is to a degree, uncharted territory, and we weren't sure if there even was a treasure at the end. In fact, it was possibly worse than that, because it was uncharted land that we knew had dragons and krakens and all kind of monsters. So the primary goal of the first experimental phase was to convince ourselves first, and eventually the community, that this driver had potential. And this could not be achieved as like a pure thought exercise. So we needed to actually implement all the features that seemed kind of tricky or even potentially could be absolute blockers for the driver. And that's how our journey started. And I would like to share with you some of the challenges we have encountered along the way. So before, in the previous slides, I mentioned that wine drivers need to take care of multiple aspects of the integration with the native system. But at the core of all those aspects is the event handling, and this is the first topic I'm going to present. All right, so time for a quick refresher of the Wayland event model on the client side. So Wayland clients create connections to the compositor, so that's through a socket. And through that, they can issue requests or receive events. So on the event side of things, so the incoming direction, there are two steps. First of all, we read from the socket. We get event data, we deserialize that, we figure out which Wayland object is the target to that event, and then we queue that. So that's the read prime there. We can create multiple event queues, and each Wayland object may be associated with a different event queue. So the second step is the dispatching of events, which for Wayland refers to calling the function the user has set to handle that event for that particular object. So we do that with function callbacks. And as long as we're careful and don't step off the well-trodden path, at least not too much, things tend to work nicely, even in the multi-threaded case. There are still pitfalls, especially with multi-threading, but that's what we have, and it's quite usable at the moment. Now for a quick overview of the Win32 message model. So events are messages in the Win32 world. So each thread that needs to interact with the user interface gets a message queue. And windows created by that thread get assigned to that message queue. Now, each thread is running its own like small message loop, and it dispatches events. So it reads from the message queue and sends them to the windows. Dispatching in Win32 is a bit different than Wayland, because we don't have a callback mechanism. We have a single function, the window procedure, which receives the message type and some arguments, and basically then we have a huge switch statement that handles the message. All right, so that's how Win32 does things, but how does Wine integrate that message loop with the driver? And that's done by the process event callback function. So the idea is that each time the application would block waiting for a particular message type, so that means that there's no such message in the queue, Wine will ask the driver if it has any new messages of the type. It calls that process event function, and now if the driver has new events, it places them in the message queue. If not, the application and returns back like a positive reply back to wine. If not, the application then may sleep until something wakes it. This all depends on the particular Win32 API function that was called. So that's something that could wake up the thread is the driver itself informing wine that it has new events that need to be processed and that could be interested in. And so for wine X11, that mechanism that wakes up the thread is basically the connection FD. So wine X11 gives the connection to the X server, the FD of the connection back to wine. And when that becomes readable, wine knows that perhaps there are new events and it wakes things up. All right, so that's the two models. And well, how can we integrate them for wine Wayland? So as a first attempt, let's follow what all the other drivers are doing and follow this process event design. And in this case, each thread that has a message queue also gets a WL event queue. And we ensure that all Wayland objects created by that thread are assigned to that queue. Now, when the driver calls back to us, we just dispatch the thread and handle events, and that's done. Simple, right? But wait, what about that mask argument, so the type of events that we need to care about? Because in Wayland, we have no way to filter the events that we receive. So we have no choice but to dispatch them all. And then, in the end, things work out because we can mark if any of the match or any of the events that were dispatched match the masks, and then we can inform wine core with the right reply. So we don't react to the process events callback exactly how other drivers are doing it, but it's good enough. So what about sleeping and waking up? Wine X11 gave wine that FD to the connection, so perhaps we can do the same, but how many of these do we have? Well, wine X11 creates a different connection for each thread that needs some kind of user interface interaction. We cannot do that in Wayland. Well, I mean, we could do that, but this won't work because then objects that are created from different connections cannot be combined or referred to each other. And we might need that because, for example, we have a window in one thread, a window in another thread, and want to make them like a subsurface of the other. So yeah, all in all, it's workable, perhaps not great, but another benefit we get with this approach is that all events that have to do either with windows and surfaces on both sides, both on the Win32 and Wayland side, happen in the same thread. So we need to care less about synchronization, and the ordering is better handled in this case. But what about input? So Wayland is somewhat special in that input events are not events on surfaces, but rather events on a dedicated input object that is somewhat like roaming transiently associated with surfaces. So in this picture, that poor mouse has no idea which queue it should be dispatched from. We can't select like one particular event queue because we don't know what the thread is doing if it even has like a proper main loop. So one idea would be, well, perhaps the ideal situation would be to kind of translate that to a per surface event kind of situation. And so the input events would be dispatched from the thread that has the window that has the focus for this particular input device. That would be probably doable, but it seems kind of tricky. There are ways to switch, like during runtime, to switch the queues objects are assigned to, but perhaps we can do better. One other idea would be to instead have all GUI threads handle input events. So yeah, many mice here, and we just react only to the events that are related to each thread. So all handlers are called, but some of them just return because they realize that, it's not their job to do anything at this point. Again, perhaps not ideal, but and of course rodent infestations are never good, but it's workable. But wait, what about outputs? So it's the similar story again, but we do have another consideration here. And the fact is that there are window API calls that need monitor information, which we can only give through WL output, that do not require the user interface, that don't require integration with the user interface. That means that that thread may not have a message queue, an event queue, may not have nothing. So, but fear not, because we all know that there is no problem in software engineering that cannot be solved by adding more threads, and that's exactly what we do now. So we have a new thread that processes WL outputs events. So how does that seem to you? I like the whole thing. Yeah, good? Yeah. I mean, we started with this neat abstraction that kind of matched what other drivers were doing, but in the end, we ended up with mice all over threads. Yeah, it's a bit complex. But one thing that we have established is that we need probably a different thread for at least the outputs. And let's explore more about this, and let's say, okay, what if all events are dispatched from one single thread? So how would I evaluate this? It's certainly simpler overall. A benefit of this is that we don't need to go through the process event mechanism at all, because we can just put events in the message queue, and that is enough to wake up threads, so we don't even need to register FDs with wine core to wake us up. It provides a total order of all the Wayland events, and because all events are happening in the same thread, we need less locking for that. But on the other hand, we need more locking because now multiple threads may interact with like the surface, like the backing surface structures that we have. Yeah, there are some other issues. Ask me more if you want to know more about this. But okay, so enough about event integration. And by the way, the previous approach was what we had in the experimental branch for a while. It served us well, but this is what we have in upstream, and I think it's much better actually. All right, so what about outputs now and output handling? So outputs are, or rather, I guess, monitors in the Win32 world are arranged in a virtual screen space, which is based on physical pixel units. All applications have access to this arrangement and can and do use it to make decisions about their own placement, like notably about becoming full screen. Okay, so that's what Win32 has. Let's see what Wayland has. Yeah, so yeah, Wayland core at least has absolutely nothing. For all we know, outputs could be arranged in a 4-dimensional space near a black hole, and that would be fine. We do get information about the mode of an output, so it's like a physical size in pixels. So at least we can use that to get the correct sizes and create monitors of the correct size. And potentially we could then do some arbitrary arrangement like by side. And it would be probably workable for many cases. All right, so actually we can do a bit better because we have the XDG output protocol, which many people don't want, but we do have it, and it does provide us with some interesting positioning information in what it calls a logical compositor space. So in many cases, that logical space will match the physical pixel space, so we can use that information directly, and all is fine and good. But often, in the case of scale outputs, for example, the logical and physical pixel spaces don't match, so what to do? One option is to just use the logical space for everything, and that actually could work for many applications. It's fine. Unfortunately, doing this prevents Win32 applications from using the full resolution of the monitor, because as I said before, applications have access to that arrangement and size and monitors, and they do use that to make decisions about their own sizes, for example. So the alternative is to stick with physical pixel sizes, but try to replicate the arrangement from the logical size in the monitors, like the virtual screen space. And this does provide the full resolution, and the trade-off there is that mapping from like logical space to virtual screen space, if we like blow up things that are scaled up, then there's no really correct way to do that. but we do have an algorithm that has great, I would say, excellent results, at least for like not super exotic cases of placements. So it should be enough for probably the majority of the users. Related to outputs, we have display mode changes. So Win32 allows arbitrary applications to change the hardware display mode. And this is mostly useful for full screen games, of course, at this point. And although Wayland doesn't support this for good reasons, it does provide excellent facilities to emulate this. In particular, it allows clients to request that the composer scales their surfaces to a particular other size. We do that with the WP viewporter protocol. So here, how it would work, and how it does work in the experimental driver, because we haven't yet implemented that upstream. So first of all, we expose a variety of common modes that applications may want to use that can fit into our native Wayland mode. When an app requests a mode change, we just accept it. Everything is fine from the application perspective. Everything is changed. The virtual screen arrangement is changed also. And when it is time to present on screen, we use the WP viewport to scale up the application, the surface of the application. And this is particularly nice because it's completely transparent to most of the other driver code. The exception is that we now have multiple coordinate spaces, and we need to take care of that to ensure that we're handling things in a proper coordinate space. But other than that, it works great. And another good thing is that in the full screen case in particular, the Wayland composer will place the bars around correctly, so everything is really very easy. All right, so that's enough about display. And I now welcome you to the Twilight Zone, because I'm going to talk about window management. So at the core of this, of the difference between the two systems, we have a fundamental disagreement about how window management works. So Win32 follows the 80s, 90s approach of being prescriptive. So applications tell the system exactly, and in an excruciating detail most of the time, what to do with a window. In most cases, the system does accept what the application tells it to do. On the other hand, we have Wayland, which follows the more modern and descriptive approach. So applications tend to tell the system what the Windows, for example, state is, or rather what they want it to be. And then the composer makes decisions based on that. So an implication of this prescriptive versus descriptive difference is a matter of control. So in Win32, applications have almost full control. In the Wayland world, the composer has more control, and the idea is that the user then, through the composer, has more control. So again, a primary example of the differences between the two systems is full screening, which is completely different in the two systems. So in Win32, the application query the outputs, position themselves to cover a particular output, and that's full screen. In the Wayland case, applications request the full screen state from the composer, possibly on some particular output. But then the composer is free to deny that request. And yeah, tough luck for if you're an application. So let's see now some more concrete examples of how we handle window management. And let's start with top-level windows. So top-level windows in this context are windows that perhaps may have some kind of decorations, but the main point here is that they are controllable by the user in terms of position, size, and this is a natural map for the XDG top level, and indeed that's the Wayland object or abstraction we are using to back Win32 top level windows. So when Wine tells us that it's time to interactively move or resize a window, we just feed that request directly to the composer. And in the resize case, the composer may react with a series of configure events. And in the move case, it doesn't do anything, because we don't have a global coordinate system, we can't request a particular position and also cannot access our position. And that, of course, creates problems. A big part of window management is, for top-level windows, is state and size synchronization. So the two systems have their own idea about what the state and the size is, and we need to synchronize. Changes may come from either direction, and we need to handle that. So I mentioned just before that we can't actually access our position in terms of where a window is in the Wayland world, but we can get a very coarse position synchronization idea, and that's implemented only in the experimental branch. Because we do have surface leave and enter events from particular outputs, and what we can do is track those and kind of like warp the windows in the Win32 side in the origin, at the origin of the windows that we think that the window is actually in. So yeah, that may sound a bit hacky, and it is, but it tends to produce like reasonable results for applications. All right, so here is an example of window management that is initiated by Wine. So Wine asks us to maximize. That ends up in the driver, in a driver callback that tells us that to change our position, perhaps in size along with state. At that point, we check like the window state and the backing surface state, and we realize that, oh, okay, so there's a difference. And then we request the maximized state from the compositor. The compositor eventually replies with a configure event. That configure event could be a denial of our request, but it doesn't matter. Then we call back into Wine again using high-level APIs to update the size and the state based on what the compositor has told us. And that's especially needed in this case because set maximized has very strict size constraints. And then finally, Wine gives us back like some notification that, okay, this is a new state, and we apply that. And at that point, we figure out, there's no difference, for example. So we don't get into infinite loops, don't worry. And then we have a compositor-initiated change. That's simpler. The main reason it's simpler is because basically Wine cannot really deny a request, so we don't have a negotiation phase. So the compositor tells us we're maximized. We update, we tell Wine core that we need to update the size and the state, and it gives us back the final size and state, and we basically apply that. And that's, yeah, window management mostly. But before we move on from top-level windows, I would like to mention one of the problems caused by the lack of position synchronization due to the lack of absolute positioning. So let's say that we have an application and a surface on the Wayland side of things. It's completely visible. But for whatever reason, it's not completely visible like within the virtual screen space of Win32. If a user clicks at the point in the window that's outside the screen space, Wine will clip it to the edges of the virtual screen space. And that will lead to a very confused and probably angry user. It is really very annoying. We don't have a really good solution for this at this time. We have been discussing with upstream about things to do. So that coarse position synchronization that I mentioned before of putting windows at the origin kind of helps because it ensures that windows have, well, they're likely not outside the virtual screen space and can take advantage of the whole screen space. But yeah, that's kind of a hack. All right, so next up we have transient windows, and by that I mean pop-ups, tooltips, menus, and in general, windows that the application has more control over in terms of the position and size rather than the user. And many of these are conceptually positioned relatively to some other window, let's say the parent window, although that term is a bit overloaded in Win32. So of course the natural mapping is WL subsurface. We're not using, for example, XDG pop-up and other more heavy abstractions because those kind of lead to some behavior on the compositor side that we may not want. So yeah, the problem is then that on the Win32 side, the position of such windows typically, even they may be conceptually relative, is expressed in absolute terms. And we also do not get enough information about who their parent may be. And even worse, we typically don't get direct information about their transient nature. There's nothing to tell us that this is a pop-up. So in order to overcome these obstacles, we resort to heuristics. So for example, we might say, well, a window that is on top, that's set to be on top all the time. It's relatively small. It doesn't have like top bar elements and captions and stuff like that. That could be like a transient window. And again, who is the parent of that window? We can guess based on heuristics, for example, like the overlap, the activation state of some other window, or perhaps which window was the target of the last input. And I must say that relatively simple heuristics like this have worked really, really well in the experimental branch. But of course, any attempt to map between the two worlds in terms of like incomplete information like this is inherently imperfect. So there are some concern about using those heuristics in upstream. But at the same time, one thing is clear that at least with the current collections of Wayland protocols, we don't have any other viable choices. So that's that. Now, for going to input. So input is relatively straightforward, except for the issue with the virtual screen I mentioned before. We translate from surface local to virtual screen coordinates. We send events like as hardware events to Wine. We can handle cursors that we can fill with bitmap data or from a Wayland theme, if that's available. A problem here, though, is how to deal with applications that set the cursor position. And this is not something that's inherently supported by Wayland. But, well, in reality, warping the cursor around on screen is not typically very useful, except in very particular scenarios, even for Win32 applications. And that scenario that it's mostly useful for is relative motion. And here is how it works. So the app constrains the cursor to a particular area within its usually client area, and then centers the cursor to the middle of that area. So then as the cursor moves, it receives events in absolute terms, but because it knows what the beginning position was, it can infer relative information for that. And then it moves back, uses set cursor position to move back the cursor to the center, for example. So the trick here is to realize that the only reason the pointers warp back to the beginning is to allow enough space around the cursor for movement in order to be able to get that absolute and then relative information. But happily in Wayland, we do have a protocol to provide these relative position changes, and we can also constrain the cursor. So it's just a matter of detecting when to switch to this relative motion mode. And again, we can use heuristics like cursor visibility, like clipping, whether the application is using, in fact, set some position to force the cursor to a position, to a particular point in the window. And perhaps simpler would be to use relative motion all the time, and that's enticing. I have tried to do that, but I have seen some drift. Perhaps I was doing something wrong, but if that works, it's even better because then we won't need the heuristics. And yeah, that's for the mouse. And now for keyboard, well, this is the shortest slide because basic operation is generally straightforward. The major complication is that we need to map key maps from XKB key maps to Win32 keyboard configurations. So then we'll be able to emit the correct scan codes and virtual codes that applications expect. So in the experimental driver, we copied effectively what Wine X11 was doing, some like algorithmic matches between key maps and keyboard configurations. But luckily, Upstream is experimenting with a simpler solution. Remy Bernon actually recently from Wine Upstream is working on that, so perhaps we can avoid that. Nice, so yeah, input, We're done with input, and now to GL and Vulkan. So the driver's goal for GL and Vulkan is basically to translate between WSIs. So for example, we translate between WGL and EGL in our case, and between Vulkan Win32 WSI and Vulkan Wayland WSI. One complication here is that under Win32, when WGL, for example, and Vulkan target a window, they target its client area, and everything that's rendered then appears there. In Wayland, because we deal with full buffers, we can actually, we can't actually do that. So our solution is to use a subsurface over the client area for GL Vulkan content. We'll make it desync, so we can keep drawing on that, and everything is fine. So GL front buffer rendering is another issue. It's used in a special way. I won't go into details because I apparently have exceeded my time, but ask me later. But yeah, things are generally fine and straightforward. Except for the matter of cross-process rendering. So under Windows, it's a free-for-all situation. Like processes can render into the client areas of other windows. And this wouldn't be too much of a problem, except Chromium does this, and then Chromium embedded framework applications do this. And it turns out a lot of like game stores and launchers, for example, use this, so it would be nice to support that. That's, yeah, kind of tricky to implement. Wayland actually makes this easier than other systems because we do have separate buffers and buffer objects we can pass around. And this is how it works, again, if you want more information. So in the experimental branch, we have a protocol based on message, window messages to do this. So ask me more if you want more information. All right, so these were some of the challenges. We're now in the past the experimental phase. We have started upstreaming. And I considered the experimental phase a success in the sense that it showed us that there's a viable path forward. We are now continuing with the upstreaming with a goal to build a Wayland driver on solid foundations so it can have a long and fruitful future. And closing, I would first like to thank contributors to the experimental branch, particularly my colleagues, Leandro Ribeiro and Sergio Andres Gomez de Real, for their great work, the many brave people that tested this in the community, and also the wider community for embracing this with excitement. I would like to thank Wine Upstream, first of all for Wine, which is a fantastic and tremendous feat of engineering. Especially, I would like to thank Remy Bernon, who has been my main reviewer for the upstreaming work and has been providing excellent guidance and insights. And last but not least, I would like to thank Google for supporting this work and helping the whole ecosystem move forwards towards a Wayland-only future. And that's it. Questions? I'm happy that everything was so clear. Oh no, something wasn't clear.
I'm curious to know, since this is still very much work in progress, can you tell yet, or do you have an estimate, if this is going to be a fully viable alternative to running the X11 driver on X-Wayland? Or will there be use cases where Wayland might be too limiting to actually support applications properly?
Right, so I would say the second. So there are unless we come up with some new protocols, there will be cases where X-Wayland would be the way to go. But the experimental branch has shown me, and possibly, hopefully, the whole community, that these cases are actually fewer than we may have thought before. And I mean, if you have an application that does very exotic window management and stuff, then perhaps it won't work properly with Wayland. But still, I mean, I was able to get LibreOffice working, GIMP, like Win32 working, so I guess, yeah, who knows?
Yeah, hi. Thank you a lot for working on this. Have you looked into like drag and drop and clipboard in general, or not yet?
Sorry, the drag and drop?
Drag and drop and clipboard, like selection, clipboard?
Yeah, so the experimental branch does support copy-paste in both directions. I didn't mention that here. And drag and drop in one direction. I don't remember which direction now, but only in one, probably from Wayland into Wine.
Yeah. Do you need to resort to hacks to kind of figure out what the drag icon looks like and stuff like this, or is it mostly straightforward?
Well, it was relatively straightforward, but again, in the context of the experimental branch, perhaps when it's the time to upstream, something would have come up with I haven't thought about.
Nice.
And by the way, most of the things I've mentioned about, I have published a series of YouTube videos. You can watch many of them, and all of those features are in. So you can see them in action.
What about window decorations? Are they provided?
Okay, so window decorations at this point, you'll have like the pure Win95 experience when you run the driver. That's retro stuff. So there have been some thoughts about, for example, using libdecor, but it doesn't really match how the driver works and needs to integrate with Wine. So I don't see that coming anytime soon. I think the next possible step is to be able to enable compositor side decorations. That could probably be one thing we could do.
Thanks.
Hi. So as far as I know, there's no guarantee that the compositor will actually draw all of a subsurface if it is overlapping with the main, extending beyond the main area of the original window, which is usually not an issue in floating window managers, which will do that happily, but with tiling window managers. Is this something that is taken into consideration when choosing via the heuristics if this is another top-level window or transient window, or not at all?
Yeah, no, I'm not taking that in experimental branch into consideration. So you mean we have a top-level window and be a bit like on the side or outside? Yeah, that's not taken into consideration. But the thing is, by using W subsurface, we are letting the Wine side of things position things, let's say. And if things match more or less, like if the positions match more or less, it will be visible at least, not ideally, but
yeah, I'm just concerned about submenus going off the window or something like that.
Yeah,
so
yeah,
that's the one reason why XG pop-up might be very nice, as long as you can deal with all the constraint stuff, because that would probably be drawn correctly.
Yeah, and certainly this could be worth exploring. That for some windows that we think XDG pop-up would be a good match, could use that. It would be not too complicated, I think, to give it that role instead of subsurface.
Thanks.
All right, so no more questions, I think. So thank you very much again for attending this talk.
Hi, hello. Hey, I'm Arek. You probably know me as Ivel. I work with co-weavers on Proton. You probably know me from that, or like being on the Xorg board, or from organizing the previous XDC. I am going to talk about wine and windowing, especially on X11, and how hard it is. So, disclaimer, expect a lot of cursed stuff, and there's a lot of weird things going on that Wayland doesn't have to deal with. So what we are doing here, we're trying to layer API. So basically you have 38-year-old API that just amalgamated a lot of stuff over the years, and we are trying to map that on even older API, and both of them kind of evolved in different directions. Luckily for us, X11 is kind of the same level as Win32, because Wayland is, you just seen what Wayland does, and other challenges that it comes with that. So the thing that was mentioned that does all of that is Wine X11 driver, which translates the X11 world into Win32 world and vice versa. The thing about it, it's extremely fragile. Basically, getting up contributions into it upstream is very tough process, like getting through reviews, getting through all testing on different window managers. And whenever you get anything upstream, usually that's a reason for celebration, and I mean that literally. And after that, usually what comes is regret, because you broke something on some obscure configuration that was working for the last 20 years and now doesn't. So yeah, there's a lot of things going on there. So let's talk about a little bit of nastiness around X11. Let's talk about mode setting. We try to map the concepts from one API onto the other as close as we can. And as you can see, this is what happens, because there's mode setting in X11, there's mode setting in Win32. The same thing goes with Gamma. You probably run some game, like older DirectX game, that crashed or haven't exited cleanly and ended up with like weird sized desktop, and then Gamma was all blown up, or like weird things happening. So we are trying to avoid all of that, and we have something in Proton that's downstream that's called full screen hack that tries to mitigate some of this. Because like it's never pleasant. So basically we introduce a level of abstractions that's not part of the upstream wine. We would like to maybe have it at some point in upstream wine. We'll see how that goes, but current shape is not really upstreamable. So the idea is that you never mode set. You try to do image scaling, accelerated whenever you can. And there's also ladder and pillar boxing going on demand if you need that sort of thing. There's also Vulkan shader for scaling that we have. There's OpenGL Gamma shader because it's mostly for the older games that use WineD3D for DirectX 1 through 8. It's quite large, 2,800 lines in just the Wine X11 driver, and 1,100 lines in the Vulkan loader. It's kind of nice thing, but it's not really necessary with X-Wayland. And also X11 is still everywhere. Hello, NVIDIA users. And it's downstream specific to Proton, so that's something that just we spur users of that. So next thing, let's talk about inconsistency. So we say that X-Wayland fixes things for us, but it has also its own quirks. So let me paint you a picture, and by a picture I mean like a simple 20 by 20 pix map, and we'll have a window, and we'll make that window green. We did the buffer flip, and like everything is fine. Let's now switch color to red. Red's painted again, and let's do a buffer swap. So we switched from green to red, and we're currently red. And let's guess what happens if you try to copy area. So we are copying 20 by 20 pixels from upper left corner to that pix map, and then copying it back onto the window. If you think that it will stay red as it used to stay, then you are thinking X11. This is what happens on any of X11 window managers. But if you start thinking Wayland, suddenly you copied the pixels of the front buffer, then painted them on the back buffer, and somehow flip happened without you requesting that explicitly. We have discovered that in Cyberpunk 2077, probably you've heard about that game, where the launcher was flickering horribly. It's built using Qt Web Engine, it uses OpenGL rendering, and for whatever reason, it does bitblate 2x2 square on the window like every 1 second. So basically, the damage tracking is broken because of that, and it updates the wrong buffer, and then it flips when it shouldn't flip, and then like flickers in very weird ways. So we've reported that against Gamescope. We really don't know what to do about that. Like if somebody wants to poke at it and like tame the snakes, then please do. Currently, we're just said like hack it, and we are forcing software rendering for just the launcher, and like it works. So let's talk about fragmentation. Let's talk about window managers. So that's mostly solved now, right? We had awesome spec that was like WM spec. The goal of it was to unify the window manager hints across GNOME and KDE, and everybody was on board. And when you look up that in DuckDuckGo, Google, or whatever other search engine of your choice you have, you're going to end up on this page. And like it looks nice. There's a mailing list. There's version 1.4 draft 2. That's the latest one available. So things are moving. Yeah, if you go to the mailing archive, they mentioned that it's obsolete since October last year. And basically, it should be superseded by GNOME's discourse, but there's nothing related to this on that. And if you look at the repository, it hasn't been updated in 9 years. So it's probably a done deal, right? So why the version is 1.4? If you poke at the repository, it turns out it's 1.5. And just the wiki page that we've landed before on is updated because you should go to specifications.freedesktop.org. And actually, the latest version is 1.5. And so I opened an issue about this, and like maybe we should take down that wiki page, maybe we should do something about it. And back in the days, like we were talking MetaCity days, 10 years ago, most of the window managers had actually like a compliance file mentioning that they implement this version of the standard, and people cared about it. But since then, since we have Matter now, since other window managers have updated, nobody explicitly like mentions the standard other than like maybe a little bit comment in the source code about things being broken. So not sure what to do with that. And the question that I posted in this issue is also, yeah, can we contribute to it? More on that a little bit later. Or is it considered a done deal and like don't touch this thing anymore? So speaking of window managers, let's talk about Matter and some issues we have with that. You probably recognize the thing. People like racing games, and people like having fancy racing game setups. So they build a chair, they have a screen, and quite often they add extra screens on the side. So you have like a side window view, you have like your windshield view, and usually this is a one window that spans multiple screens. And WM spec has an awesome thing called NetWM full screen monitors, which allows us to span a window like that. Yep, it's great. It does the exactly same thing what we should do and what we expect it to do. The problem is it cannot be unset, and that's part of the spec. So this breaks behavior on multiple window managers when you suddenly go from multi-screen, full screen to a single screen or like a window. Because then suddenly moving the window is hard, and suddenly you cannot move it to another desktop. Weird things happen. So for balance, let's talk about KWin. For example, KWin doesn't allow moving window where you have NetWM state full screen set. So sometimes applications want to move a window. So let's go to settings. Let's switch which display the window should be on. So we just move the window and it's still full screen, right? It works on all the window managers except for KWin, so we have like a little bit of special casing. But to be honest, we cannot blame that on both of the compositors anyway, because this is weird usage case. And this is not specified as a part of X11 or any of the libs or any of the protocols or any of the specifications. So they have a freedom of do whatever we want, and this is just something we have to deal with because we are translating low-level API into another level API. So let's talk about matter again. The thing is that also whenever you try to map a window, it unminimizes, which is sensible thing to do because you map a window, and also it's not a part of the standard. And also, who would do that? We do that, and we have a use case for that. So basically, we have to re-minimize that window again. It's weird. Let's also talk about some games, because there are some nasty games, and let's talk about focus string prevention. You probably had an issue when you launch game and it wasn't unfocused for some reason. Yeah, so what do? There was this game that starts with far and ends with cry primal, and it started unfocused, the taskbar was visible, and that only happened on KDE. And after manual focusing, so if you clicked on the window, controller didn't work. And what's going on here? We were trying to figure out how it's going on, because on GNOME, on every other window manager, it was working just fine. So I take a look at what the game does, and this is the sequence. So it creates 1x1 pixel window, then it shows it, then it minimizes it, then does something for 2 seconds, then it restores that window, then it resizes it to the full screen, then it does something more, and then it requests to focus that window. As this is a production program that I wrote to make sure that it's focus link prevention, and this is this behavior that does that. And I'm looking at that and yeah, this is the thing. This dance they are doing. What's the reason for that? What can we do about it? I was considering doing workarounds, ignoring some of those events, but that would be a very brittle hack just for a single game. So after a little bit of consideration, I decided if I was a window manager, I would also find that suspicious, and that's fine. So we just instead made a partial fix to make sure that the focus state is synchronized between us and the game, and the game knows that it's not focused anymore. And then when we refocus, it's actually the controller works, because they have weird logic related to focus where it just toggles the controller support. So when you unfocus the game, it toggles it, and then when you focus, it toggles it again. So if you end up desynchronizing the state, suddenly the controller doesn't work when it's focused, but works when it's unfocused. So in all of that, let's also talk about GameScope. GameScope is our savior, kinda. It's designed for games. It uses Wayland, and it's really designed to work with what we are doing. We even expose some extra hints and style information to as a window properties, so they can make better informed decisions about what to focus or how to handle layered windows, because that's also another kind of worms. And it works great. That's basically the use case, and everybody now wants to have it integrated in Steam and just run your games through that as a nested compositor, because it works. So the question is what we do from now. My conjecture is that desktop X11 is kind of solved, and by that I mean nobody pokes at the dark corners, because you have toolkits, you have GTKs, you have Qts of this world that basically are very uniform in what they are doing, and they are well tested, and they are supported by all the window managers. But then there comes Wine with Wine X11, where we poke at the dark corners of XLib, and we are doing things that nobody else is doing. And that was never tested, used in any scenario before. And then we also have this driver. Because of that, any change to Wine X11 can cause a butterfly effect and breaks a lot of other stuff. So since it's impossible to get things exactly right without more extensions and WM involvement, what do we do? Do we resurrect WM spec? Do we introduce another spec where we expose more of the wine state or wine 32 site state and let window managers to start implementing support for that? I have no idea if you have suggestions, if you want to fix that Wayland bug that I mentioned, or if you know what we should do now, just let me know. And yeah, so I work for Codeweavers. If you want to work on Wine, we are hiring right now. Do you have any questions?
Oh, is it working? Okay.
Yes.
Can we get the GameScope specific Wine window properties in upstream? Because quite a lot of users end up using Wine with GameScope, and that ends up having a completely different focus situation where some things don't work. And we really rely on the Win32 window styles to make good informed decisions in GameScope.
Yes, and I would like to be the case. That's not up to me. I'm not a maintainer of Wine. I only deal with like the Proton stuff. I think like trying to standardize them a little bit, like, and provide documentation instead of just saying, hey, this is what we are doing, you can use it. So people actually know what they are looking at, because like not everybody is familiar with Win32 world, would be a good step forward. And like also we could ask other window manager and compositor authors if they are interested. I think that would help this case. It would be awesome to have that upstream though.
Hi, thanks for this very entertaining talk.
Thank you.
Can't we just fork the Wine X11 driver into a Wine X Wayland driver to get more stuff upstream and to never touch the kind of working X11 code again?
What do you mean by forking?
Basically just copy it, don't modify the version that runs on normal Xorg, and patch the X Wayland one.
I guess that would be also bad in a way, because then you have like two places where you sometimes have to fix things, because we still hit like legit bugs, because like some new game uses Win32 API in entertaining way. So we have to fix that in Wine X11. So that means now you have two drivers that you have to fix, and you have also all the special casing. It would get confusing pretty easily. So I think it would be better to just integrate that into the current X11 and like do a little bit more special casing. But that's also not very nice. So that's why most people nowadays, I guess, don't use upstream Wine. They use Proton and Proton offsprings, just because they allow for all of that. And we try to maintain that and make sure that it all works. Whereas upstream tries to be a little bit more Puritan.
Yeah, hi.
Hello.
I'm interested in the more long-term solution to all of this mess. And I've been thinking for a while, and I'm wondering if, like, we're trying to make Win32 into either X11 or Wayland or like a different API. So there will always be an impedance mismatch. There will always be cases where it will not exactly like match the Win32 semantics, and we need to like do some workarounds and whatever. So yeah, I'm kind of wondering if we could have like use Alexandros' work and the Wayland thing, and completely whip out the part where it talks to XDG shell, and completely replace that with Win32 shell. Like, you still get the same ways to pass the buffers and get input and all of that, but the window management part is completely mirrors what Win32 is doing. And then GameScope and maybe other compositors, if they want to, can basically have a perfect view of what Win32 is expecting, and yeah, that will be like completely mirror Win32.
I think this is a valid approach, and it has been kind of explored through two venues. First one is with Wine X11. You have something called virtual desktop. So basically, it creates window, and like this is your desktop, and everything is inside of it. It's not perfect, and it's not exactly what you're saying, but like this is the way we explore that, and it doesn't really suit well some other use cases outside of games, because for games it's mostly fine. Like you want to run GameScope, which is another, like, I guess, partial venue of that, because we have like better cooperation with them, and we expose those extra hints. But there's a bunch of people, for example, that use it, Wine and other stuff for office work, and they want like normal desktop window applications, not full screen games. So they want proper integration with your desktop environment, which is like a regular desktop environment. So the answer historically for that was to try to do the mapping as good as we can and hope for the best, instead of trying to like those more confined implementation approach.
Yeah, I think we should have both. Like we should have a best effort mapping for like everybody else, and we should have something very specific to Win32.
I think it's a pretty good approach. The question is, will it end up in upstream? Because if it ever, if it won't get accepted and it's something that you would need to maintain, for example, in Proton downstream, that's not a fun thing to do and not really sustainable. So
yeah, absolutely.
Definitely worth discussing. I'm not sure how smooth on that because the virtual desktop feels kind of neglected anyway. And this was already like an attempt on fixing some of the X11 issues.
Yeah, thanks.
What's missing from upstreaming the so-called full-screen hack?
It's that it's just very invasive and very, very large. As I've said, like it's 2,800 lines, which in terms of Wine X11 is a lot. And it's mostly focused on full-screen games. And we don't really know what it breaks with desktop applications, and Wine is also used for that. As I have said, Wine X11 is brittle, and people are afraid to touch it. And upstreaming anything there and the amount of testing necessary just takes forever. So we've just decided that the pain of rebasing it is more bearable than actually trying to upstream it. And as I've said, like it's not that necessary with Wayland, because the viewporting there and the isolation provides is pretty great.
Yeah, I mean, to expand on that, I think it was never a goal for us to upstream full screen hack, and we were always picturing that in the future something like GameScope would be integrated better and address that issue.
Yes, that's definitely a case as well. Like it was from the beginning, from the inception, a temporary solution for Proton. There are some voices that it would be useful because Wine also has a macOS backend, so it renders there as well, and they could use something very similar. That's people from upstream, that people working on that were talking about it, but I'm personally not involved in this, and I'm not very interested myself.
There is a question from Matrix. Would Wine Wayland be a better driver for Proton?
Can you repeat the question?
Would Wine Wayland be a better driver for Proton?
That's an interesting thing. So far, I don't think so, because like it's still in very early development and it still requires a lot of extra protocols. Maybe with some extra protocols it would be good, but I don't think it would provide any benefit when it comes to like rendering times or like saving. Like we would save maybe one copy with it. And there's like another kind of worms where you would need to test all the games or a backlog that we know that works with Wine X11 on Wayland. And yeah, just the amount of missing protocols and how untested it is and how big the game library is, currently it's not really feasible. In the future, once it matures, definitely worth considering, but not for now.
Not really a question, but to just answer Tomeu's thing about the full screen hack, it's not really needed on Wayland or any Wayland compositor because we have WP Viewporter there, which basically does the same thing on the compositor side.
Yep. Okay, I think that's it. Thank you.
Okay, so cool, it's working. Hi all, I'm doing the secretary talk for the state of Xorg or the union or whatever, because unfortunately Lyude couldn't make it because of some last second emergency with a cat. And so Eric and me did the slides, or well, Eric did the slides and I did the talking. So first, huge thanks to Igalia and everyone for organizing a great XDC. Bit more like enthusiasm, please. Yeah, great work. Especially because we kind of didn't have an XDC last year and they jumped in to fill the gap. It took us a bit a challenge to restart things after Corona. We had, well, this is short. We had 12 sponsors today. For this XDC, and we had one travel grant. I guess people don't quite like traveling so much, or maybe there's more corporate travel budget. But I mean, the money is available, so for next year, just submit a talk, and you can sneak in a travel grant with that. Thanks a lot to Arek for handling all the invoicing there and stepping up as treasurer. We had a pretty full-packed program this year with like 12 full-length tags, 18 half-length tags, 2 workshops, and a massive pile of lightning talks. So big thanks for everyone who submitted something, because that's what makes XDC happen. And maybe as a reminder, we have like this workshop track, and this year we only got 2. It's available. It's great for having discussions, a bit more in depth, hackfests, whatever else you want to do. For next year, the request for proposals for XDC is still open. We're kind of still looking. We have something-ish probably in North America. But also, like, XDC is a fairly big conference, so it takes a lot of work to organize. And we would like to be back in Europe in 2 years, so anyone who's like interested in hosting it, please reach out. We try to also contact possible volunteers so that we can have a nice XDC in 25 too. And also, like, we're also looking for sponsors. We have a nice sponsorship level, so I'll probably start annoying companies again later this year. For infrastructure, we're still struggling with costs. It's for those who've seen like the board meeting, our GitLab infrastructure is expensive because it's been ridiculously successful, and just the server costs that are sponsored in like terms of service without going over books, it's $250,000 a year. And unfortunately, because we don't really have that much money, we rely hugely on volunteer effort, heroic volunteer efforts by our admins to cut down on costs. We had like almost 30,000 in Google Cloud Engine last year, and this was a bit too much for our budget, so it was migrated, which unfortunately caused an outage, but that cost should be now down to 0. There's also other migrations going on to enable IPv6 and move to a bit cheaper data center, because even if it's not on our books, like the servers are very expensive, and we need to make sure that the companies that are sponsoring us are happy with the deal. So Equinox also has a huge shout out here. But really, like, the biggest shout out is to our volunteer admin teams. We're trying to fix this, and especially Benjamin Tissois. So I think that's also a huge applause for. Because yeah, like, we have a bit of money thanks to XDC, but it's not gonna be enough to pay for the infrastructure if you would not have so many sponsors and volunteers. Next up is code of conduct, transparency reports. We got 7 reports over, like, I think mostly GitLab, but there's also the conduct at address, I think it is. And one of them resulted in a removal of a user. So a bit more, I think, than last year, but still fairly little. GSOC, second time in a row this time. We had a bit of struggle over the pandemic. 5 students, everyone passed. Yay, someone presented here. Huge thanks to our mentors and Trevor Werner and Christopher Michael for coordinating the entire thing. It's always quite a bit of work. On internships, the not so good news is that unfortunately our EVOC program, the kind of stopgap, what we can cover with GSOC or Outreach, is on hold because SPI wants to do this properly with an employment contract, and that employment contract is unfortunately not yet ready. This also meant that one potential internship fell through the cracks, and like huge thanks from all the people in private on the board to mentors for trying to catch the fallout a little bit. On that is kind of a nice segue into our parent organization. Thanks everyone for voting this year. So we managed to buy a hair past the bylaw changes to move to Software Freedom Conservancy. The transition is in progress. Like Software Freedom Conservancy is a lot more serious about doing things properly. So we're crawling through all the contracts that we have and everything else we have and make sure that the workflows and processes work and we can do everything we want to do with them. Fingers crossed that with next year's XDC we can do all the financials over conservancies. And that kind of brings us to the foundation. If you're not a member yet, please sign up at members.x.org. Like anyone in here cares enough about what we all do to definitely be qualified to sign up. And what you get is you can vote on stuff, make sure we can do changes like join conservancies. Bragging rights, there's access to certain specifications that we can only share kind of privately, and probably the most important thing is submit Chronos conformance results for all the drivers that are developed by the community. And finally, we're always trying to make XDC better and relevant for the community and the people attending. So if you have feedback, if you want to say something done differently, please send us or talk to the organizers or anyone from the board here at board@foundation.x.org. We've also been talking a bit yesterday about what we should change maybe. So one idea that's been floating around is that we reduce the formal talks part of the program a bit and try to make the hallway track a bit bigger with maybe a hack fest or perhaps just promoting the workshop track a bit more. So if you have ideas, if you've seen things that are really good that we absolutely need to keep, or things we need to improve, please give us that information so we can make the conference better. And that's it. So if you have any questions, otherwise it's, I think, coffee break. This one.
So when we did all of the stuff with Chronos before, we did that through SPI. So do we have a plan to get Software Conservancy into the Chronos membership position and we sign all the same paperwork, whatever that was?
Yeah, I mean, this is one of the list of paperwork things that we need to make sure is all checked and crossed and I's dotted. And it's definitely, I would say, the most important contract that we need to carry over. But yeah, that's one of the things. Otherwise, I guess, coffee break. Thanks a lot.
Okay, so we are going to start in a couple of minutes. I will ask you, sorry, I will ask the Lightning Talks speakers to come to the front rows so we can do it quickly, the change. The thing is, we have 5 minutes per talk, no questions. There are many talks back to back, no time between talks. So hopefully we can do it quickly and we don't spend too much time. Guilherme is about to start in a minute, so yeah. Thank you.
Okay, sound test. Okay, so hey folks, thanks for the presence here. I'm going to talk about crash kernels, a bit of a typical topic here, right? Not graphical, but as Linux users, I guess most of you already face the crash once in a while, right? I am Guilherme Piccoli. I work at Igalia, doing core kernel stuff, and currently I'm working on the Steam Deck. So the context of this presentation, the Steam Deck is the well-known game console from Valve, and it has a Linux distro called SteamOS, which is Arch Linux based. So Arch has no official tool for collecting kernel crash logs. There's like a wiki, very explained steps, but it's manual. We don't have a tool for that. And so we have, that's something that would be really nice in SteamOS, to be able, if the gamers face some crash, to collect some data, but what data? And at what cost, right? We want to be lightweight, to not waste resources, but we want to have enough data. So the message maybe, right, the kernel log. So little talk about what a kernel oops or panic is. So oops is when kernel detects an error, a bad condition, and the panic is like the reaction of the kernel if that's set. For example, you could set it to reboot. Usually it's like that. Some potential panic causes are null pointers, not like code null pointers, but concurrency stuff. Imagine one code is writing, the other is reading, but there's no good locking. So it could cause a panic. Lockups, soft lockups, hard lockups, hung tasks. For example, hard lockup is when kernel code is running in an RQ context for too much time. So other tasks cannot run, right? So you can configure a panic in these cases. There is the artificial triggered panic through sysRQ. We do that for testing stuff. Bug clause in the code. And what can we do when we face a panic? We could do nothing. It's usual, like forget about that. But it's interesting, if possible, to collect data, to take this opportunity and collect some data, like a VM core, which is a memory image of the broken kernel or the message, right? So we have 2 ways of collecting such data. Kdump is the first one. Is basically the broken kernel jumps to another kernel that collects the full memory of the first kernel. It can compress this memory image, cut the free pages and whatnot. The interesting thing here is that it's almost a full copy of the memory, but it's good for post-mortem analysis, for example. But the main con is that it requires a bunch of pre-reserved memory, usually 200 megabytes for newer kernels. Also, there's risks booting the kdump kernel, and PCI devices might be in bogus states, and we don't have a standard reset mechanism in x86, etc. So it's good, but has cons. Now, collecting most of the data, the pstore mechanism is different. So it happens when the panic happens, the pstore might save the message in some persistent area that we call backend. We have multiple backends like RAM, UEFI, variables, block devices. It's lightweight. It's used on embedded device on Chromebooks. it does not require, for example, KExec support, which is good for like embedded device with secure stuff like Qualcomm. It's very fast, hopefully, and transparent process during the panic time, and requires almost no memory, or no memory indeed if it's like UEFI backend. For RAM, oops, you can reserve like 1 or 2 megabytes. The cons is that it does not save a full VM core. So we save like the message. So both infrastructures, KDump and PStore, are kernel technologies. They require some user space counterpart to set that up. So we present here KDumps, which is the tool we're working for actually. It's a generic tool that is PStore and KDump. It's available on the user repositories, supports Grub, support both Unity CPU and Rakut. We plan to support system deboot soon. It defaults to PStore, removes backend, but we have plans for UEFI, and it's very customizable. CCTL, we can set the CCTLs for panic and the crash kernel parameter. Right now, it's the default tool for SteamOS. It's present on the deck as the tool for collecting kernel crashes. So that's it. Thanks a lot for your attention. Feel free to reach me on IRC or email. The cable, I don't know.
Okay. Hello, everyone. I'm Julia Zhang from AMD. So I'm going to talk about dGPU prime feature on Zen guest VMs. So on OpenGL and Vulkan, dGPU prime allows an integrate GPU to display render data, display output data rendered by a discrete GPU. But on Virtual and Venus, it doesn't support DMA and import or export. Also because Zen guest VMs need to use memory copy to sync up data from guest to host, so it will cause low performance. So we come up with a new design and implement of dGPU prime feature on Virtual and Venus. So let's look at our platform. We use Zen hypervisor plus QEMU to launch DOM 0 and DOM U and use integrate GPU and discrete pass-through GPU. So this is our design for OpenGL. We use iGPU to create display buffer, and iGPU would send command to host side to create hosts local resource on host side and IO vector in guest side in kernel virtual GPU. And then dGPU would import this buffer to dGPU and as a display buffer. And after that, we have display buffer and render buffer, and every time Mesa swap buffer, dGPU would bleed data to iGPU, and iGPU would send a command to host side to sync up data from IO vector to host side to the pipe resource. So for Vulkan, we use the same idea, but we include some differences. First, we use GPM to create buffer object on iGPU, and as same as the step 1 of virtual, iGPU would create IO vector inside the kernel driver and send command to host side to create pipe resource. And after that, dGPU would import this buffer, this GPM buffer object as foreign memory of linear buffer of swap chain. And after that, Mesa would send command to copy data from guest to host, same as Virtual does. So with this feature, we now can run applications which require different level of performance, but we still face two challenges. First is that actually AMD GPU require 256 aligned stride. So at first we use hardcode, which is same as existing logic. But now we also come up with another method, which is to create IO control to send to host side to query the correct thread. Another one is that actually because Virtual and Venus depend on memory copy to sync up data from IO vector to host side, so every time it's a buffer, it will send command, but this will cause very low performance. So we, instead of this, we use blob memory, which can get the mapped pointer to guest set, and with this, guest set can bleed data directly. So after that, we also enable this feature on native context. So dGPU, pass-through dGPU this feature can be enabled on both of pass-through dGPU or two VirtIO GPU. So with this feature, now we can see the comparison between Virtual and Virtual plus blob memory method. We can see a big improvement of Virtual plus blob, this method. And this is a result of Virtual plus, Venus plus blob memory. We can still see a big improvement. This is our repo and upstream merge request. Please refer to them. And at the end, I want to say thanks to Bob and Daniel from Collabora for giving me a lot of idea and support. And thanks to Ray and Pierre-Eric from EMD. And thank you all for listening. If you have any questions, please discuss with me offline. Thank you very much.
Jessica, are you there?
Yep.
Okay, give me a second. Okay, yes, you can start, please.
Awesome, thanks.
Can you hear me? Oh, hi. So, I'm Abhinav Kumar, and along with me is Jessica Zhang. She's attending virtually. Jessica, can you hear me?
Yep.
Okay.
I can hear you.
We both work with the Qualcomm display team, and we would like to share the talk on the solid fill planes. Yeah, we can go to the next slide. Yeah, just to give an overview of the Qualcomm display pipeline, we have any typical chipset would have a combination of a few SSPPs which would be blended into a single frame by the layer mixer, which would go to the DSPP. And then we have skipped a few blocks for the purpose of this discussion, but then that would go to one of the interfaces, which could either be a DSI display port or the write back. Obviously, SSPP is the source surface processor pipes, and DSPP is the destination surface processor pipes. In this discussion, we'll be focusing on the SSPP because we can program the SSPP to either fetch from memory or skip the fetch by programming it in the solid fill mode. And Jessica, who implemented this feature, will go over how she did this. So it's all yours, Jessica.
So in addition to the hardware optimization, there are some user spaces that also will allow users to mark specific layers as solid fill. So for example, the Android hardware composer HAL has this solid color hint, which can allow users to do that. So on the right-hand side, you see like an application that has a pink solid fill plane on the bottom, and then a solid fill color hint in the layer dump. So we, in a combination with both the hardware optimization and the user space solid color hint, we were actually able to see a bit of power savings when taking the power measurements of the vanilla Google Chrome and Messenger apps in comparison with that of the, a simulation of both of these app UIs where we split the solid color and the non-solid color layers into different planes. We actually see up to a 37% decrease in power usage, specifically in the Messenger app. Next, I'll be talking a little bit about the implementation. For context, this is the current state of the solid fill plane series. It's gone mostly reviewed buys and act buys from both user space and driver developers, with the remaining comments being about very specific implementation details. However, the higher level implementation has been pretty much solidified at this point. So for the implementation, we have two different properties. First, the pixel source enum property, which will allow users to specify different types of pixel data sources. For example, the solid fill or the frame buffer source. Next, we also have the solid fill property blob, which will allow users to pass in a 32-bit per channel RGB color. And finally, we'll loosen the DRM atomic checks to allow for non-frame buffer pixel sources. And finally, this is just a sequence diagram for how to do atomic commit. So first, the user has to set a solid fill pixel source and also set the solid fill property as a valid solid fill color blob. In the atomic commit, the driver will check for the type of pixel source. So for frame buffer sources, it will continue with the current behavior. That being for non-null frame buffers, it will do the atomic commit. For null frame buffers, it will do a disable. For solid fill pixel sources, if the solid fill color is set to a valid solid fill blob, it will do the atomic commit. For no solid fill color blobs, it will return an error. And finally, if the pixel source is none, it will disable the plane. And if you want to follow the current discussion on the series, feel free to check out the series on the free desktop patchwork or in the email archives. And for a written overview of this feature, please check out our blog post on the Qualcomm Developers Network. Thank you so much.
Thank you.
We good? Hello everyone, my name is Charlie Turner, I work for Igalia, and I'm going to give a status update on the Vulkan video ecosystem. So for those of you who might not be familiar, Vulkan Video is a video acceleration API exposed as a set of extensions to the Vulkan standard. Several APIs have been proposed across the convenience, control, portability space. The ones that tend to offer high performance are often locked into a specific vendor or are not particularly portable. And those ones that try and offer both performance and portability have struggled to gain wide industry adoption. So the hope here is that we can piggyback on Vulkan's momentum across the industry to try and solve these problems. So the API is vendor and platform agnostic, it's stateless, so a lot of the heavy lifting is pushed to the application rather than the driver. It offers very fine-grained control over processing and scheduling of video operations. And thanks to Vulkan's design, it's possible to implement highly parallel frame processing across both the CPU and the GPU with a very fine-grained control of the synchronization between frame operations, both of which are absolutely critical for good performance. It also seamlessly integrates with the Vulkan graphics and presentation layers with copyless sharing into both of those subsystems. And it's designed to work on the smallest of systems to the most powerful servers. And some uses of these extensions, some applications you could say, the ability to use compressed videos as an efficient streaming source for data to be mapped onto 3D geometry, and that's useful in game engines, desktop compositors, things like that. The new hotness of generative AI models uses a lot of encode and decode operations that can be fruitfully accelerated with these sorts of accelerations. When you're decoding video, you're often dealing with per pixel motion vectors, and this information is useful for a number of real-time rendering algorithms, such as deep learning supersampling, denoising of ray tracing. You've got your typical use cases of streaming, which is obviously useful to offload, various GPU filters that you might want to run on decompressed frame data can all be kept in the GPU memory. And there's also applications in immersive experiences like light fields and extended reality and other such topics. So 2022, last year, I would say was the year of finalizing the codec-independent APIs, so building a really solid foundation to add further codecs and other extensions. So going into 2023, we had this good foundation. AVC and HEVC decode was finalized and shipped. The focus there was just simply due to the market share of those codecs, nothing particularly philosophical. AV1 is in active development right now as we speak, and VP9 is on the roadmap. One problem we did have was in the CTS. It turns out that parsing bit streams is a pretty tricky problem. And the way that was initially approached was to incorporate a binary library that caused a lot of problems for users of the CTS. So at Igalia, we tidied that up. NVIDIA kindly released their parsers in source form, which is a nice self-contained set of files for doing bitstream parsing. And we've also extended the coverage of AVC and HEVC significantly. And 2023's focus, going towards the end of it, is to finalize the encode APIs for AVC and HEVC, as well as working on some other codec extensions. To give you a bit of a flavor, this is still quite provisional. We're focusing more on correctness rather than performance right now, but already we're seeing fairly strong signs here. So I took a fairly popular test vector here, the Sintel track. This is in the AVC high profile. And FFmpeg has already implemented the Vulkan video extensions, and they were getting about a 2x speed up versus VA API, which is another popular acceleration API in the industry. And the NVIDIA sample app, which is sort of an example of how to use the extensions, was getting 3x on top of Vulkan, so 5 to 6x on what is currently out there. And there's some provisional frame timings up here. They're a little bit, take them with a bit of a pinch of salt because timeline queries aren't actually supported on the decode queues, but this is what I was getting on a 3060 Ti GPU. I'd say 4.3 milliseconds for 4K frames is pretty decent, but the speed of light there is around about a millisecond. In terms of what are the drivers looking like, so for AVC and HEVC, the open source drivers here, the Intel Anvil driver is completely passing the CTS, looking great. RADV is pretty close, it's just one test failing on a pretty weird case. And the proprietary drivers from NVIDIA and AMD are passing on Windows and Linux. There's also an AV1 extension. It's in the form of a Mesa vendor extension. The Kronos version is in works, it's cooking. And if you're familiar with the Fluster test suite, there's a lot of quite complicated test cases in there. And for a hardware-accelerated API, getting that kind of pass rate in Fluster is pretty respectable. One of the best pass rates I've seen with the RADV driver. The community adoption, am I out of time? Sorry, so the community has adopted this. It's in FFmpeg 6.1. It's going to be coming in GStreamer. Check out that Wicked Engine blog post. We're going to be working on AV1, VP9. It's really difficult to use this extension, so we're hoping to create libraries to ease that. There's some problems on Android that if anyone knows about it, please come and talk to me. And there's much more going on. Bunch of references if you want to get involved. Thank you.
Oops. So, I start? No. Okay, so hello, I'm Alejandro Piñeiro, I work for Igalia, and in this presentation I'm going to talk about how we use gfxreconstruct and apitrace for performance evaluation. So when 4 years ago we started the Vulkan driver for the Raspberry Pi 4, our first objective was getting Vulkan 1.0 conformant, and after that we did a lot of work for performance. We made that more later, usually after each conformant at the 1.1 conformant and getting 1.2 conformant, but was there when we did a lot of work on performance. So at that time, what we focused the performance work on Unreal Engine 4 samples. They were pushing a lot what the Raspberry Pi 4 was able to get. They were really generally GPU limited, and they were using really expensive shading. So that means that most of the focus of this implementation work, performance work, was done on the compiler. That has also the advantage that it also benefited the OpenGL driver. So this is rendered by the Raspberry Pi 4. This is one of the Unreal Engine samples. So what the process at that time was, we get the sample running, we capture the shader code, we identified non-optimal code traces, we figured out what we could do to improve that, implemented an optimization, and then we need to verify the outcome. We use etnaviv, we use manual testing, and we also use gfxreconstruct and apitrace. So those are tools that they allow you to capture the calls to the API, so Vulkan calls in the case of the gfxreconstruct, or OpenGL calls in the case of apitrace. So here we have a port of DOM 3 on one side and Unreal Engines in the other side. What was the two main uses for these tools? One was visual checking for artifacts, because sometimes when we were doing some improvement, we suddenly get some artifacts, but were not, in some cases, were not like, okay, everything is wrong, but like we were, going in a corridor, and for example, some flowers or some lighting effects, instead of seeing it that correctly, have some blinking that were not correct. So we needed to visually checking for that. And having the traces allow us to just put in the tries to run and just we was looking for it. And we also use that for performance comparison between before and after the improvement using the FPS. We created a script for that, so we have all the traces in one directory, the script took all the traces from that directory, and with time, we started to add some parameters. Because, for example, on average, we run these traces several times, and we got an average of the frames per second. Advantages. That made visual checking far easier, because the alternative was like putting the sample and started to fake playing the game, going for corridors, and that was boring. Also, in the CI, just in case someone is wondering, on the CI, there are some cases of having some frames and checking the outcome, but that was, as I said, that was not enough, because sometimes you need to, go into the corridor, and the artifacts were not always in the same place. Also, the frames per second was really easy to understand, and at the beginning of performance work, it was evident for some specific improvements to see that it was a really improvement. The problems. The frames per second is unreliable. For example, if you run the same trace with the same things, sometimes you get a different value, because there's a lot of things that can affect the frames per second. And now that we did this performance work, getting just with the frames per second, if we get an improvement is minimal. So at this moment, we use this frames per second measure, we use that mostly as a sanity check. we implement an improvement, and at least the frames per second shouldn't go down. Well, this is the contact. Sorry for talking so fast, but this is an allotted talk. So this is the end.
Yes. Good. Here you go. Well, hello. Nice to be here. My name is Philipp. Who am I? I work for Google as a site reliability engineer, actually manager there. So what I do for my day job, especially I run, or my team runs a Google Cloud IAM authorization, and doesn't have to do anything with X11 or Mesa or Wayland or anything. However, I find I don't do enough coding, so I figured out I need to do a bit of tinkering along the side. And I've been using Linux kind of in professional environment for like half my life, but never did contribute anything back, so I'm trying to be here and trying to basically consider this my feeble attempt to basically address some of that. So why particularly am I here? Kind of Wayland, after many, many years, is finally getting to the point of replacing X11 in main distros, which is cool, but also means kind of for me, who is really stuck in some of the old world with like window managers and stuff, is just really, it's replacing stuff that I've grown fond of using, so I figured out I'll see what I can do to replace some of that. What brings me here kind of is back in X11, there is icons or a thing, basically applications, there's a protocol for window managers, the ICSymmetry protocol, that Windows can define icons as a name or pixmap, or even a window can configure sizes using an orchestration protocol. And so basically any application can just define the icon they can be using, and then the window manager will they make use of it to display it in whatever the appropriate size. Turns out on Wayland there is no such thing at the moment, because Wayland is, it's about having cross-text subshell and so on and so on. So what used to be there, the applications can define their icons, doesn't exist, and that's something I like doing. Particularly fun thing was on X11, applications actually would abuse this icon protocol to not just show the icon, but basically in the code of like a window manager and so on, or window maker, and some of the window managers there was using this for small apps. They were really showing docked state, and so Billy could use this as kind of application visualization. So that's the background of what I'm missing, because Wayland doesn't have this. So what I'm proposing, basically I'm hacking around with, to basically have a Wayland protocol extension that permits applications to declare a surface as an icon, and then compositors can pick that up and display in the appropriate space. So yes, basically that we have, again, a way for applications to define an icon, and basically also not just have it as a static way, but also have a surface that can be shown. There is a protocol kind of hacked around, kind of somewhere on GitHub that you can tinker around with if you want. Also there is, I've gotten it working, so I have an application that shows a surface on the screen, which is amazing. So there's ways of having an app that shows a surface, but it can show some application state in there, and then a compositor that actually can bind and show it. So that's basically status that I have there. So it's proposed, I have a protocol, and I have it working in a prototype. It's still prototype, so kind of what's coming up, what I'm trying to do next is to figure out a way how to upstream that thing, whether it's going to WL routes, which I'm basing my work on, or to Wayland, I have to yet figure out. Then of course also clean up the stuff that I'm doing, the app and the compositor, to really get that out, and then at least we have a basic state working. If you have been working in that space, there's kind of, that model so far works well if the compositor itself is basically placing the icons. However, in the new world, many dock applications like in Swagger, so they're separate binaries, so we need to figure out another protocol to actually then the compositor transport the icon back to the particular docking application, but that is something next to follow up with. And then, yeah, they figure out how to associate things with the application. Good. And I have 1 minute left, but actually I'm over with what I wanted to say, so if anybody's interested, please reach out. That was me. Thank you for listening.
My name is Helen Koike. I'm a senior software engineer at Collabora, and we'll quickly talk about stop merge regressions, the merge workflow. Let's start with the basis. What is CI? It stands for continuous integration. It is about automating the execution of tests, and it's more about just writing the test itself. It's about all the infrastructure around it. We basically have those two types of workflows, post-merge test and pre-merge test. In the post-merge, we have tests running on top of the latest tree and report failures for future fixes. But now imagine that you are a developer that just got your patch merged, and the CI reported some failures, and you start thinking, well, it works for me, I have other things in my priority list. It's probably an error of the test suite itself, or maybe it's just an error of the CI infra, I need to check, or it's probably not affecting many people, it's just a corner case, so I'll check it later. And this happens more often than you think, so this starts creating a forever increasing backlog full of unreliable bug reports, and then CI can be easily neglected, and people start ignoring its results because they just don't trust it. On the other hand, we have pre-merge tests. So the patches only gets merged once all the tests passes, so it prevents introducing regressions, and it forces developers to fix the tests and the CI because their patch depends on it. With this, we get all the CI advantages, the quality assurance. It can also speed up development. You can spend less time setting up testing environment for all use cases. You can have a good coverage on different hardware that you don't possess in other environments. It can speed up merge cycle since you don't need to wait for the tested by tags from other developers, and you don't need to wait from someone around the globe to test in some hardware that you don't have. But there are also some disadvantages since your patch depends on all the tests passing to get it merged. It starts to become very sensible to infrastructure instabilities or overloads and to long execution time, and it can be frustrating sometimes. You can also have flakiness that decreases trust. I mean, by flakes, the test that sometimes passes and sometimes then they don't, and it's not necessarily because of your code, it might be because of the test or because of the infrastructure. So it has the potential to wear out developers and increase stress levels. To mitigate that, you can use a combination of both. You can choose to have a lighter pre-merge test that won't test everything and compensate that with a more complete post-merge pipeline that takes longer and can run in more appropriate time. Let's focus on pre-merge tests. So who is Marge? Marge is a merge bot for GitLab. The idea is that the only user who merges patches into your repository will be Marge. So developers prepare their code. They can manually trigger the CI. Developers can then prepare, say that it's good enough, submit and open a merge request, reviews provides feedback, then the code is considered good enough, someone's then assigned the merge request to MargeBot. MargeBot rebases the patch and triggers the CI. And if the CI passes, MargeBot is happy to merge your patch. But there are some bad days. There are a few times that planets just don't align and you have lots of instability in the infrastructure, and Marge just refuses to merge it, and it's not the fault of your code, and you ask her again and she refuses, you ask her again, she refuses again, and eventually she merges it, but every run that Marge takes can take a really long time, and you can see how frustrating it can be. Marge is working with several projects. We have Mesa CI, Mesa 3D, we have a few projects in GNOME, for instance, Moot, Epiphany, Loop, GNOME Shell extension. We also have Pulse Auto, GStreamer, Glasgow, Haskell compiler, the blockchain Tezos, Octez, Free Desktop SDK, and I wish we could have an integration with mailing list or patchwork, so we could use in a few subsystems. So I particularly enjoy the Marge one, the non-Marge, and the Haskell compiler, because if you look at her face, it feels that she's very determined to do her job. So give Marge a chance, get involved, and thank you.
Well, I'm Sergi, and I'm doing a job doing an upref update revision of the projects. That is when you have a Mesa inbuilt generator or something like that, and you like to update it and have it the newest dependency version. This is a project that is in FreeDesktop in CI, in graphics CI. What we do is first the same thing that a developer does is try to find a good candidate for the dependency, a good newer release of the dependency, and then prepare the changes, the minimal necessary changes to the CI to say from now on try to use this other release. And launches a pipeline to see that everything is working fine, and if it's necessary, with the results of this pipeline, it updates the expectations and prepares a merge request eventually with this new dependency reference and the expectations. In case something is wrong and you cannot even update the expectations because something failed deeply in the test, then it can create an issue. So you can track every day when this was broken and when this has been recovered. So it's easy to see in Virgin, for example, that for updating the expectations, you have to go job by job and see the artifacts there, check for the failures, do the things by hand. In Mesa, the pipeline is much bigger, so the problem is much bigger. And even now that we are working with the RMCI, we see the same thing. So this thing of collate is not a feature that is only for the upref. So we split it out and make it a separated tool that the jobs, you can take the information from the jobs, the traces from the jobs, the artifacts from the jobs. We are especially interested in the results CSV and the failures. So one of the things that is in the work in progress that would be released soon is that for any of your pipelines that you are working that you have to update expectations, this tool will be able to provide you a patch of the expectations for your case. And that's all. Thank you.
Is that the end? Yes.
Yes, I'm going to let me prepare it while I put the full screen. And is in the other, is in the extended.
Sorry?
I mean, do it and then you have mirror. What kind of setup you put?
It's going to be the same.
Is extended view, so just you need to change it to mirror, I guess, or what?
I don't know how to do it. I never use macOS.
Yeah, I guess it's there, display.
Okay, so over the last few days, several people have come to me asking me, so I'm Eric Engstrom, I'm one of the two Mesa release maintainers. And over the last few days, several people have come to me asking me what I actually do as a release maintainer and how much work that is. And it sounds like people are interested in knowing more about that, so I figured I would explain a little bit. And please come to me if you have any question, if you're interested in doing this. So what we're talking about is the meta releases. So the development model is roughly that the devs work on the main branch. I mean, they work on their own branch, but then they merge that into the main branch. Some of those commits are bug fixes and are tagged as such. And then some magic happens, and in the end, the users get, every 2 weeks, the latest batches of fixes, and every 3 months, all the new features. So there's a bit of magic in the middle. What is it? So from the release maintainer's point of view, so the commits get tagged by the devs. We have a tool called PickUI that gathers all the so that's a tool that we wrote, that gathers all the commits, figures out which ones are relevant, and so relevant for the old branch that we're looking at, and presents us with a TUI, so a terminal, to do the backports. From there, we pick the commits one by one. We do some fix-ups if that's needed, which is rare just after the branch point because it hasn't diverged yet, but the longer you wait, the more the code needs to be fixed up, like the code that moved around, or a helper that was added that didn't exist yet, or things like that, or renames like near dev or stuff like that. And if we can't do that, then we ask the original dev to, sorry. We ask the original dev for help. And once that's done, we do a local build to test that it actually works on our own machine, enabling all the drivers for the build, but some of the drivers don't build on ARM, for instance, which is my machine. And if it works locally, so we do that for all the commits, and if it works locally after a bunch of commits, usually I do 20 to 30 commits per batch. We push them on the staging branch, so staging/x.y, and doing that triggers the CI. And the CI is the main tool of the release maintainer because you can't test yourself on all the hardware. So we send it to the CI, wait a few hours because it takes a very long time. And if it fails, then we have to figure out the problem, which might need, so we have job logs, and like sometimes it's easy to figure out what went wrong, or at least what commit is the guilty one. But if we can't, we might need to bisect, which means just doing a subset of the commits and sending that to the CI, and again, waiting a few hours to get the results back. And yeah, same, if we can't figure it out, we ask the original devs again. And once everything looks good, and it's the scheduled time for a release, then we use the xorg release.sh scripts, which is actually used by a lot more projects than just the xorg project. And so that creates the tarball that's uploaded on the website and signs it. We push the x.y branch, so not the staging one, and we send an announcement email to say that the new release is available. So the question, again, that was asked is how much work that is. That depends. So I do that 2 to 3 times a week, because obviously the longer you wait, the more you have to do. And like I mentioned, batches, if they're small, it's much easier to bisect if you need to do that. And so just after the branch point, it's roughly like 2 to 3 times a week. 15 to 30 minutes, and when the release drags on like the last one, and you have to do point releases a lot, it ends up being maybe 1 or 2 hours, 2 to 3 times a week. So it can become a lot in the end. And yes, you can help. Please help. If there's anyone interested in doing this, I didn't paint a very nice picture, but to be realistic, it does take time. And if anyone is interested, please reach out to me. Dylan is probably also available for questions, but yeah, ask me if you want to know more. Thank you.
So I'm filling in for Tomeu. So he's got to catch a train. So I'm here to do his presentation for him. And we're covering the Vivante NPU driver. So it's what is it? So it's an accelerator for neural networks. So with the AI being so hot right now, like, you know, tons of people are doing it, but there's no really open source solution. So we Tomeu designed a Mesa delegate for TensorFlow Lite, and then basically it passes the description of the TensorFlow model down to the Gallium drivers. The Gallium drivers synthesize the necessary operations to run the convolutions from TensorFlow, and then run those on the hardware units on some socks that are available. So the Vivante NPU, if you guys don't know, is a Baryshkov piece of IP. So the tensor operations are currently done on the CPU. There are tensor units, but they're not supported yet. They're going to be supported soon. Let's see. Yeah, so the other operations, so you have convolution operations which are done on the NPU right now, and then the tensor operations are done on the CPU so far, but we're, that work is continuing. So we can run MobileNet v1 not in close to upstream Mesa with full accuracy for that resolution. So we're already 3 times faster than the CPU at around 34 milliseconds. And a lot of that is because of 21 milliseconds for the tensor operations. And then once Tomeu finishes the work on the tensor operations, that's going to drop down significantly to about 14 milliseconds, which is very close to what the proprietary blobs perform at. So, so in terms of upstream, there's patches that are still 2 small patches that are offset. Still a lot of cleaning need to do before the merge requests into Mesa gets sent. And then from a long-term, from a short-term perspective, work to do is the tensor operations that I just mentioned to cut down the time by 60, 70%. And then storing the immediate tensor results into SRAM. So there's a 1.5 megabyte of SRAM in the NPUs themselves. And then they drastically speed up operations, continuous operations. Also, you get a lot of zeros in these convolution matrix multiplies. So both compressing the zero weight, zero weight, sorry, I forgot the term, but the encoding for encoding multiple zeros at once. With that work and some skipping the zero multiplication works, you can get a lot of speed ups as well. So we should be able to get close to the blob's performance. And longer term work is the modern operations. So the NPU is relatively old, so it only supports certain convolution and tensor operations. And a lot of the newer models have other operations that cannot be supported via fixed function hardware. And then there is one programmable unit on the device that can be used to do these operations. And then also, right now, it's targeted as a TensorFlow delegate. So a future target would be an NHAL, so which is directly used by PyTorch Mobile and ONX2. And then that way, the NHAL would have a delegate to the TensorFlow Lite. And then MobileTorch can directly use the NHAL. So this work can be expanded to other NPUs, such as Qualcomm's Imagination, ARM. Like a lot of vendors are creating their own NPUs because like most of the operations are relatively simple from a hardware perspective. And also MediaTek, who's using Cadence, and probably Synopsys has some NPU that I don't know about. And then on OFTC, Tomeu has a channel, and then if you're interested in this work, you can find him either at the email below or on the IRC channel. And then finally, last but not least, we have a live demo. And then, so this is MobileNet v1 running on the board here with the NPU. So we finished in 39 milliseconds. So the CPU takes 100 milliseconds, so we're about 3 times faster. And then once the tensor work is done, that'll drop down to about 12, 13 milliseconds. So if anybody has any questions, feel free to ask offline. I'm not the best resource, but I can answer a few questions. And then Tomeu is a great resource for all this work. So thank you, guys.
Hi everyone, I'm Michał Savic from Canonical. I work on the Mir team. I borrowed this presentation from Chris, who ran it on our Ubuntu Summit last year. Testing with WLCS, which we aspirationally named, that's the Wayland Conformance Suite. So yeah, why do we need this? When we decided to switch Mir or to support Wayland on Mir, we wanted to have kind of, black and white, you're doing things right. And we didn't find anything that other than the text in the XML protocol descriptions, which is, the protocol is only valuable if it keeps the promises and that all of the implementations do it. So we went ahead and kind of programmed a test suite against Mir and made it a separate project. The compositor provides a plugin, so you create a plugin that adapts your compositor to this. WLCS is a binary that you supply with that adapter plugin. It's used to start, stop the compositor, inject input, manipulate windows when necessary, depends on what the test is. And we support a number of protocols already. We have more than 1,100 tests now. And the test running process, so you can, debugging them is relatively simple. You can just use GDB. Previously, one of the questions was whether, we couldn't run it in a single threaded compositor. That was a problem. Now we do have a way to do that. You can just inject WLCS into the Wayland main loop. So that's a help. A sample test looks like this. You create a surface and wait for it, and confirm that that the compositor does the right thing. In this case, pops up an error. In this particular case, the protocol does not explicitly state what the error is to send here, but it would be nice to have a consensus on that, and for all compositors to do their same thing. It's available in Debian, Ubuntu, Fedora, Alpine Linux. It's licensed under GPL v2 and v3. It doesn't require the CLA. Yeah, go forth and test. It's under Mir server WLCS on GitHub. We're on Matrix or discoursubuntu.com. Thank you.
So, hi, Melissa again, from Ialia. So first day we have the KMS color management workshop, and this is just a brief summary of what we discussed that day, and was mostly current status, concerns, and next steps. We got a good variety of participants, different companies working on different GPUs, and this is the name, but sorry if I missed your name to the list. So this workshop was a follow-up meeting from the April Shell Display Next Hackfest that was organized by Red Hat this year in Czech Republic. And that time was a good opportunity to put our ideas together in different point of views and put also everything on track. start to work on it. So from that meeting and also more discussions that we have in the mailing list, we already advanced on defining and implementing the next generic color management API for the DRM KMS framework, and we decided to start from the pre-blending color pipeline that is in the DRM plane. So during this Monday, we put some topics in the table, and many of them came from issues that we are already facing in the current work for exposing hardware color capabilities, such as conflicts between existing pre-blending and post-blending color properties, new generic API implementations on VKMass. Harry shared lessons learned on this work. Also, we discussed beta testing with a write-back connector, since CRC needs a perfect match. And this is the way that we use now on IDT. We also discussed the variety of capabilities for color transformations and the NVIDIA color singularities. Another topic was latency issues when update 3D LUTs. So we discussed how to handle with this, with async LUT update, and also benchmarks, and probably would be better to looking for a general API solution. We also discussed precision guarantees, some issues with hardware-specific implementations as segmented LUT. We think that bit-by-bit equalities are lost cause, and we prefer to evaluate this issue in each iteration. We also defined that it would be better to start with a very simple API and then improve it later. And also that we need, that user space needs to always be able to fall back to shader, so no implicit assumptions. And so next step that we defined from there was that we agree that the proposal that Harry shared upstream already is good enough for us, and it would be the reference start point for the next work. So we will now focus on having more vendors that will attach to this proposal. Then also check 3D LUT performance, and we also discarded the proposal to go deep with VKMass, so we prefer to start already on GPU. And then I invite everybody, because after the workshop, we also discussed here about the next Display Hackfest to keep progressing on Linux display main issues. And we will organize then the 2024 Hackfest here in Coruña. I invite you if you are interested. We'll be at the Igalia Hackfest, at the Igalia headquarters. And the tentative months are April or May. And I will reach you by email if you are in the list of the workshop participant. But if your name is not there and you are interested in participate, so please reach me here or contact me by mail. So save the date and look forward to see you next year.
Okay, hi, I'm Sasha. I'm at Google and I work on the Chrome OS graphics and compositor team. So I wanted to just give a little update on what we've been doing with HDR, where we are now, and where we're hoping to go. So just to give a recap, this is sort of the transfer function we've been using for Chrome OS for HDR monitor devices. We have an SPRG-like curve at the beginning, and then sort of a linear segment for the HDR content on the other end, and this programmable elbow that we can move depending on the sort of nits we want and how much we want to allocate to the SDR content. And for this, we use the display primaries directly for the color space. So that's been working well for us. So why bother change it? So HDR10 is the most common HDR format. It's becoming very prevalent on web content, and we're also starting to see a lot more web content, images, videos that are HDR than we had been before. Similarly, there's been a huge uptick in external monitors that have that kind of capability, and people just really have been excited to get to use these things. So for people who aren't familiar what HDR10 includes, it's 10 bits per channel, 2020 color primaries, and a PQ transfer function that is non-linear. So one of the first steps to taking advantage of HDR10 content is to set the output metadata DRM property for the connectors, which is a post-blending property that we utilize the BT2020 primaries to set, as well as the white point and different aspects, the luminance of the display. In order to set this, we have to do color space conversion and tone mapping ahead of time for the content. So it's really just the final step before sending off to the display. It's a more standard approach. It's available on a lot of different drivers, so it's been helpful for us. And the nice thing is that we get all of this information for the output metadata blob already just through the EDID, so there's not a huge amount of work to be done there. So what's more interesting is what's coming up next. So what we'd really like to do is be able to dynamically adjust the SDR white level, similar to moving that elbow joint, to be able to move with the content for dynamic metadata, which is required for HDR10+, as well as for brightness changes, ambient lighting changes, user brightness changes. We're really excited about the ability for per-plane color management. Definitely interested in the Hackfest that's coming up. To take advantage of having overlays with different color spaces would be a huge savings, and not having to use shaders would be amazing. And like I said, the dynamic metadata would be a huge change for us, making per frame changes depending on the content. So that's all I have for you right now, but hopefully we'll have more in the future. Thanks.
Let's try. Fingers crossed. Yeah, but could work.
Good work. Hello everyone, I have 5 minutes, so I will be very quick. So, content, how to be nice to others and how to test efficiently. The nice to be others part is very important, because when you start testing with our CI, you really don't want to eat all resources we need for testing. So, yeah, right, I should speak to microphone. Yeah, great. Thank you for telling me. Anyway, so when you want to test efficiently. So I guess all of you ever clicked on the GitLab CI interface and run the testing manually, and it was pretty boring, right? So we've been thinking the same thing as we developed the CI. And since we sometimes needed to test new jobs or some specific changes, we developed simple script which run only what you want, and you don't have to click even once. So, but let's start with how to not abuse it. So, first, before you start testing, you want to test on your device connected in CI. You don't want to abuse other jobs which you don't utilize. So, one nice thing is always check what is assigned to March bot, and this gives you idea how much jobs are queued and how much is the CI utilized. So first thing, you can check it by URL and decide if you want to test or not yet. The QR code is linked to the GitLab URL where you see a list of jobs to be merged. Or you can use magical script which got merged like a week ago, and it has ability to show you how many jobs are queued. So for example, if you want to do some stress testing, which we get to later, you can use the script and it will return 0 when there is 0 jobs in queue. Otherwise, it will return number of the jobs in the queue. And if you pass the wait parameter, it will wait until you get to the 0. So that's a great combination with another script we have. And that's CI run and monitor. Who knows the script? Oh, a lot of people. I'm very happy. I'm happy to hear that and see that. Anyway, so the script is like CLI interface for GitLab CI for Mesa. And it automatically triggers dependencies, automatically trigger the jobs you specify. You specify the jobs with regex. It's Python regex, not bash regex, so you have to use the right syntax. And as you see here, you can specify your jobs. For example, this is Adreno 600 anything jobs. So if you need to test on one, for example, one category of devices, you can specify it. Or you can specify multiple devices with regex. So that's nice. And also, as you see, you can use the merge queue. So it will wait until the queue is empty and then you start testing. So you will not interfere with merge, pre-merge testing. So this is not all. Let me show you how it works. So it's pretty small. I hope you see it. And this will be example. Hopefully it will work this time, because I tested it. But yeah, there is, as you see, job waiting 0. So everything got merged. Meanwhile, there was one job when I was waiting to start with my talk. So I was thinking I will have to omit it for the example case. So this will show you how much dependencies you need to run, and it will enable all of them. So this is first part. Right now, it created the job and everything. And at some point, it will manually disable all the jobs which you don't want to run. So you will save CI resources. You will not waste anything. And this will take a few moments because, you know, it's like a huge CI. So as you can see, something already succeeded, which is nice. Some jobs which you otherwise have to click manually gets enabled automatically. And I think I have 1 minute left, so it may, yeah, everything is manually disabled, what you don't need, which is perfect because otherwise when we started working on CI, I was clicking that by hand and it's like not that much fun. You see a lot of clicks here. And here you see the jobs. You see the jobs, the A630 jobs, A618. Well, at least you see some jobs, right? It's like demo, so I just hoped it will show up. And right now it will wait and show you progress as you test. You can also stress test it, so you can. Yeah, time is over. So you can also, if you show //help, you can also see what else it can do. So thank you for your attention. Enjoy.
This is just a summary of the workshop, the CI workshop that we had, well, like the CI Tron one. So I'm going to talk about the plan, the reality, and then the discussions. So the plan was to provide an overview of the system that would be a bit deeper than what the talk was about. I wanted to walk the attendees through the instructions, so how to set up the hardware, you know, like what to connect where, how to connect the PDU to the gateways, then wanted to show them how to discover a dot. So what you show in the slides before, like where you had the discover button, and then have it exposed on GitLab, and then use this dot in GitLab CI. So, and finally, I wanted the attendees to go through, to follow these instructions on the three gateways that I was providing, along with 6 dots. So that's now the reality. So there were a couple of people. I'm very, very happy with the attendance. So we were about 15. So that was good. Then we managed to set up the gateway and then the PDU. So that's, again, wonderful. What didn't work is when we tried to use the dot, in GitLab CI, it just wouldn't have any serial logs. Yeah, that's what happens when you don't test this part. Sorry, when you make assumptions, you make an ass of yourself. So, and finally, we wanted to have the attendees try it, and only Danilo managed to do that because he was, sorry, not Danilo, Dmitry. He was doing it at the same time as I was talking, but otherwise we didn't get to this point. But what we did talk about is a couple of things. So, fast boot support is one thing. So in the presentation, I was saying that we wanted to standardize the boot process, and we standardized on PXE/iPXE, or mostly iPXE. So basically network boot. Not every device is network bootable, or it could be done, but then it's just making it harder. So one type of device is phones, and then or Android stuff. So the standard there is to use fastboot, and fortunately it's possible to keep the auto discoverability of everything. So basically, if you treat the USB hot plugs like iPXE requests, then you can, when there is a hot plug, then you can check if there is, well, if it is a fastboot device. If it is, then you get the machine serial ID. Then you ask, hey, what is the boot configuration that needs to be sent, and then you just send that, and then it boots. So that's very good. Another use case is the Apple M1/2 support. So here the scenario is a little funkier because they are using the mini hypervisor, which allows controlling a ton more things than what you would normally expect, which would be just a kernel initramfs and kernel command line. You can there also well specify the, like you can chain load the MinIO bootloader itself, and then also they would like to be able to select which firmware version that they want to deploy. So that's great. And just like fastboot, they also can control the boot process through USB, and they show up with a USB device ID. So basically, we can do the same system and have auto discovery of everything. So yeah, that's doable. And finally, another thing for Asahi, they need to be able to take over some unpartitioned space between partitions. So that's have support to take over space at the end of the drive, but not in the middle between partitions. And the reason why they have that is because the recovery partition is found at the end of the partition table. And yeah, that's it. Thank you.
Okay, this is going to be fun. This is not my laptop, and this is not my presentation. So let's see how it goes. Thanks, Chema, by the way. Okay, so let's start with some housekeeping as usual. I would like to thank our sponsors of this conference. First of all, I would like to thank Igalia for organizing this conference and for being so generous of being as Platinum sponsor here. I will also thank Gold sponsors such as Google, Collabora, ARM, and Microsoft. And I don't forget our silver sponsors, FexEmu, the Linux Foundation, AMD, and Qualcomm. And finally, we have our bronze sponsors, the Kronos Group and Codeweavers. Thank you so much, all of you, for sponsoring this conference. Then we have the supporters, the Turing's Office of A Coruña. Thanks a lot for supporting this conference. Similarly, for the local Linux user group called gpool. Thank you so much. I would like to say thank you to Igalia for sponsoring the welcoming event. In case you miss it, I'm sorry, there were Galician bagpipers there. There were some music and a lot of chit-chat there. Also, thanks to the XOR Foundation for sponsoring the coffee breaks. There was the continuous coffee break all the time here behind me, and there were the coffee breaks, one in the morning and one in the afternoon in the other side. Thank you so much for the XOR Foundation. I would like to say thank you for Igalia for sponsoring lunches, especially, you see the weather, we save us, getting wet a lot of during these days. So thank you so much, Igalia, for sponsoring the lunches. I'm sorry, for once joining remotely, we didn't manage to send you coffee and lunch on the live video stream. I'm sorry. Next time, come here. We have cookies. Then I would like to say thanks to all of you for coming here and to all of people that are attending remotely. Thank you so much. The conference is for you. Without you, there is no conference. Thank you so much. I would like also to thank the organizers and volunteers team. Let's start with the organization team. Thanks a lot for Ricardo. You were managing the Call for Papers committee. You were selected, preparing the program. I mean, you are doing an awesome job. Thank you so much. I will say thank you to Chema, that guy there, yes, the one that changed the slides for this, and his laptop, actually. Thank you so much. You are awesome. You are organizing this event together with me. I think that we are a good team, and we have a future as event organizers, I think. Yeah, and finally, thanks to myself, I guess. I would like to say thank you to Lucas Friczek. Thanks a lot. And to Erika Engstrom. Both of you did an awesome job preparing the design of all the signs that you are seeing around, even this thing. I don't know the name in English, sorry. So yeah, thank you so much for preparing all the printing materials. There was most hidden work for many Igalians. These people, Pablo Abelenda, Eva Loureiro, sorry, and Maria Piñeiro, they were helping a lot behind the scenes. Thank you so much. Also, I want to say thank you to the catering company here at Palesco. I think they were doing an awesome job. They were taking into account all the different allergies or dietary restrictions that you may have. And I think they did an awesome job. And as far as I heard, the food was very good. So thank you so much. Do you think I'm going to forget you? Come on. Thanks so much for the TESEC company. You are doing an awesome job. You were very quickly fixing all the sound stuff that we're having. So thank you so much. I would also to say thank you to Kasia, who is the manager of this venue, and to Esther, who is the girl downstairs that was receiving all of you and giving you the badges if you were not joining for the welcoming event. So thank you so much. Then the XOR Foundation Board of Directors, you are awesome. Thank you so much for helping us. And I would like to say especially thank you to our free desktop sysadmins. They are doing a lot of work that you are not seeing, and this is because they are doing an awesome job. If you don't see any problem, it's because they are doing great. So thank you so much to free desktop sysadmins, and especially to Daniel Stone, because I bothered you too much during these days, and you were very gently to fix all the issues that I was reporting. Thank you so much. Then we have a bunch of volunteers. I don't know if calling you volunteers, forced volunteers, I don't know. So I would like to thank Charlie Turner and Andrea Almeida. You are awesome, thank you. You may not notice from the back, but there was a guy in the first row who was just putting signs to all of you with a bad face, say, you know, your time is over. So thank you so much, Iago. Thank you. Also, Christopher, Michael, and Juan, you were helping so much us. Thank you so much. Madiha and Mark Collins, you were in charge of saying loudly the remote questions, and also you were helping also with the mics, so thank you so much. But I am missing a couple of volunteers. Yes, you know. Can you stand up, Miguel, Paula? Those are students for the University of A Coruña. They are GPU members, and they were doing an awesome job during this, all these days. So thank you so much. I'm sorry if I miss you. I would like to thank our speakers. You are also one of the key parts of this conference. Without the speakers, we are nothing, actually. So thank you so much for all of you. And let's not forget the workshops, where the discussions were happening, and as you saw just a few minutes ago, is where the magic happens. So thank you. And finally, I would like to thank all of you again, because you made it to come here. I know that it's not a main hub for traveling, but I hope that that was worth it, actually. So thank you so much for coming. Just to give you some numbers, we were more than 160 people registered online. People picking the badge was 120, and then we have 25 virtual attendees. So, I mean, that's not bad. Thank you. And let's not forget the live stream people. We had more than 6,000 views on live stream during these days. So thank you. There was an official, well, I don't know, maybe perhaps next year we make it official, climbing activity during XDC. So yeah, it was a crazy idea by Charlie and Andre, and I think that we can probably make it official next year, I don't know. So thank you so much. If you notice, I always mention the local Linux user group. It's called gpool. It's very important for us because, for example, several founders of my employer were members of that Linux user group, and now it's turning 25 years old. As you see, this look is very active, actually. They organized 10 years ago the WADEC here. We organized Academy in 2015, I think. We organized XDC 2018. We organized a lot of local activities, like several days of free software, hackathons. We give talks to students. We give some labs to do some practical stuff. I mean, this local user group make us, very proud of this region, and also I hope that it's going to feed us with new contributors. So thank you so much for all of your work. You know, 25 years are too much. There are life changes, and Alejo, I know that many of you don't know him. He died 6 months ago by a car accident. I mean, I'm pretty sure if he were here, he will be helping us. So this is for you, Alejo. Okay, so thank you. Just the last thing. See you next year. Thanks.